What invisible forces set some stars free, sending them racing across the galaxy? How does motion, from runaway stars to spiraling galaxies, weave the quiet order of the cosmos? If everything moves, from atoms to galaxies, is there anywhere in the universe truly still? Surveys of runaway stars reveal that a significant fraction of massive O-type stars are moving faster than their peers. These observations indicate that ejection mechanisms are common enough to populate the galaxy with runaways. In some catalogues, nearly half of all O-type stars show signs of being runaways. These stars demonstrate how efficient supernova explosions and dynamical interactions can be in imparting speed. Runaway stars can travel far from their birthplaces. Some of the hot, blue stars visible in the halo or high above the galactic plane are runaways. Their presence in these unlikely locations tells a story of ejection. Over millions of years, these stars have drifted or sped away from regions of active star formation. Their orbits carry them on long excursions before they eventually return toward the disk. The binary supernova scenario was first outlined by Dutch astronomer Adriaan Blauw in the early 1960s. He realized that when one member of a binary dies in an explosion, the sudden mass loss can fling the companion outward. Blauw's insight laid the groundwork for understanding many runaway stars discovered later. It connected the life cycles of massive stars to the dynamics of stellar orbits in a simple yet powerful way. Dynamical ejection involves the complex physics of three-body and four-body interactions. In a typical encounter, a binary and a single star approach one another closely. Energy and angular momentum are exchanged. Often, the binary tightens and ejects the single star. In other cases, a star from the binary is swapped with the intruder. The outcomes depend on the masses and approach velocities. These gravitational dances are unpredictable in detail, but statistically produce a population of runaways. Observational evidence supports the dynamical ejection scenario. Runaway stars in the vicinity of the Orion Nebula, for example, have trajectories pointing back to dense regions where massive stars reside. These runaways do not show evidence of supernova enrichment, suggesting that their high speeds result from gravitational interactions rather than explosions. Such cases confirm that multiple pathways exist for accelerating stars. Some runaway stars exhibit peculiar chemical abundances. Enhanced nitrogen or helium on their surfaces hints at past mass transfer in a binary. In such systems, one star may have siphoned material from its companion before the ejection. The resulting chemical signature survives the ejection and travels with the star. By studying these abundances, astronomers can infer the history of interactions within the original binary. Runaway binaries, pairs of stars ejected together, are exceedingly rare. To remain bound after ejection, the pair must have enough binding energy to withstand the forces that accelerate it. Most binaries are disrupted during the ejection process. The scarcity of runaway binaries is one reason why hypervelocity binaries have not been observed. The conditions required to accelerate two stars without breaking them apart are difficult to achieve. Low-mass stars can also be ejected as runaways. In dense clusters, dynamical interactions do not discriminate by mass. However, low-mass runaways are faint and harder to detect. Their discovery often requires sensitive instruments and careful analysis. Despite being less conspicuous, these stars contribute to the overall population of runaways and offer clues about the dynamics of their birth environments. When considering the large population of runaway stars, hypervelocity stars represent the extreme tail of the velocity distribution. They are the exceptional cases where the ejection energy is so large that the star overcomes the entire gravitational potential of the galaxy. Their rarity underscores the special circumstances needed to achieve such high speeds. Understanding how often these circumstances arise is a key goal of the ongoing research. Imagine stepping outside on a clear night and gazing up at the stars. At first glance, they seem like tiny lanterns pinned to a dark dome, fixed in place and eternal. Yet every point of light is moving. Some drift in wide loops around the center of our galaxy. Others orbit companions, and still others glide through the vastness between galaxies. From the smallest atom to the largest cluster, nothing in the universe is truly at rest. We live on a planet that rotates every day, giving us the rhythm of sunrise and sunset. Our world also moves around the sun, completing an orbital journey once every year. That familiar cycle marks seasons and shapes life. Though we seldom notice it, this motion carries us through space at about 30 kilometers each second. We are passengers on a spinning sphere, whirling around a star in a cosmic dance. The star that lights our days is also on a journey. It travels around the center of the Milky Way, tracing a graceful path through one spiral arm and heading toward the next. The Sun's orbit takes roughly 230 million years to complete, so it has only circled the galaxy a handful of times since it formed. Along with our Sun, hundreds of billions of stars stream along similar paths, moving under the gentle pull of gravity. Viewed on human timescales, the night sky seems still, because these motions are so slow relative to our lives. If we could watch from a great distance for hundreds of millions of years, we would see the spiral arms turn like the whirls of a giant pinwheel. Stars would drift and swirl, forming patterns and then dissolving them. What appears static to us is part of a slow and intricate ballet on scales we can scarcely comprehend. Over cosmic distances, even small motions accumulate. Stars wobble slightly as they orbit, oscillating up and down through the galactic plane. Clumps of gas and dust slide inward and outward, driven by gravitational waves and interactions with spiral arm patterns. Every movement is part of a larger rhythm set by the distribution of mass in the galaxy. Nothing is random. Everything follows laws of motion and gravitation that have held since the universe began. Imagine billions of bees circling a hive, each following its own path, yet remaining near the group. That is what the Milky Way's stars do. Gravity holds them together in a vast disk, and their orbits keep them from collapsing into the center. The balance between gravitational pull and orbital motion creates stability. It is a state of quiet order, where the combined motions of countless stars form the spiral pattern we see in telescopes. The Milky Way rotates much more slowly than the whirling edges of a hurricane, but the distances involved make the velocities immense. Near our position in a minor spur, the orbital speed is around 200 kilometers per second. Farther out, the rotation curve flattens because dark matter adds mass that we cannot see. This unseen component guides the motion of stars, binding the galaxy together and shaping the gentle curves of its arms. Though numbers like 200 kilometers per second sound enormous, they are relatively modest compared with the escape speed from the galaxy. These orbital velocities are just enough to keep stars bound. They are like the steady flow of cars on a highway, moving quickly, yet following lanes that lead them around a circuit. In this picture, gravity is the road, and stars are the vehicles staying within its bounds. Inside the disk, Stars also exhibit random motions, drifting slightly relative to their neighbors. These peculiar velocities are like tiny eddies in a larger stream. When astronomers chart them, they reveal the history of spiral arm passages and past gravitational encounters. Even such deviations are small compared with the overall orbital flow. The quiet order of the galaxy leaves little room for chaos. On longer timescales, galaxies themselves migrate through the cosmos. Our Milky Way is part of a collection called the Local Group, where gravitational interactions are slowly drawing the Andromeda Galaxy toward us. Clusters of galaxies orbit one another, and the cosmic web stretches as the universe expands. The pattern is one of constant movement, from the dance of planets around stars to the drift of galaxies in clusters. At the smallest scale, atoms vibrate in place, and at the largest, the cosmic fabric expands. Between these extremes lies a continuum of motion. Stars form in collapsing clouds, where turbulence creates dense pockets. Those nascent suns gather planets and debris, all falling into stable orbits. The interplay of collapse and rotation shapes solar systems and galaxies alike. Motion and gravity are the architects of the cosmos. Even dark matter, although invisible, participates in this great dance. Its mass outweighs that of ordinary matter, and its gravitational pull shapes the motions of stars and gas. Without dark matter, the Milky Way's spiral arms would not hold together. The unseen halos around galaxies are like scaffolding, allowing structures to form and persist. Dark matter's presence is inferred from the motions we observe, an indirect hint that the universe is full of hidden participants. Over billions of years, the positions of stars will change dramatically. Constellations familiar to ancient human cultures will distort beyond recognition. The star we call Polaris will no longer mark the pole. The night sky is a time-lapse photograph in slow motion. Our lifespans are too short to watch it unfold. But with instruments and measurements, we can detect the subtle drifts that tell us motion is continuous. Recognizing this backdrop of motion allows us to appreciate when something extraordinary occurs. Against the quiet flow of the galaxy, a few stars move with such speed that they defy the usual patterns. They travel so fast that gravity cannot hold them, and they will leave the galaxy entirely. These rare travelers were unknown until recently, and their discovery opened a new window on cosmic dynamics. When astronomers measure velocities, they use units like kilometers per second. A difference of tens of kilometers per second can tell whether a star belongs to a particular cluster or whether it has been disturbed. In this context, a few hundred kilometers per second is typical. Stars that exceed this by a large margin stand out because they are breaking the rules set by gravity and rotation. The universe hums with gentle motion. The whisper of gravity guides each cosmic traveler along its path. Only when a star is accelerated far beyond this whisper do we hear a shout. Such a shout announces a dramatic event, a close encounter, a tidal disruption, a supernova explosion that has thrown the star off its course. Understanding these rare events requires us to listen carefully to the background harmony. It is the contrast between the calm flow and sudden acceleration that makes hypervelocity, stars, so fascinating. Against the sweeping arcs of billions of stars moving coherently, a single sun can be flung like a pebble launched from a sling. The shock of that departure reverberates through the galaxy, carrying information about the forces that launched it. The journey of such a star becomes a messenger, telling a story of cosmic violence hidden within the quiet order. In the chapters that follow, we will explore how this quiet order is established, what maintains it, and how, on rare occasions, it is disrupted. We will trace the paths of ordinary stars and then follow the trajectories of those extraordinary few that break free. In doing so, we will come to understand the mechanisms that can accelerate a sun to incredible speeds and what these events reveal about the hidden heart of our galaxy. In contemplating the cosmic sling, we confront the interplay of order and chaos. A star begins its life in a well-ordered orbit, only to be catapulted by forces beyond its control. This unpredictability is part of the universe's character. Even in systems that seem stable, deep interactions can create surprises. The hypervelocity phenomenon reminds us that nature will always find ways to redistribute energy, and that our models must allow for the unexpected. The scales involved dwarf human lifetimes and journeys. A hypervelocity star can take tens of millions of years to cross from one side of the galaxy to the other. Its story unfolds over timescales far longer than civilizations, rising and falling in its light. Reflecting on these spans fosters humility and wonder. We catch a brief glimpse of a process that has been underway for eons and will continue long after we are gone. Progress in understanding these phenomena depends on collaboration across disciplines. Observational astronomers gather positions and velocities. Theorists construct dynamical models. Mathematicians develop the integrators that trace orbits. Engineers design detectors sensitive enough to catch faint light from the halo. Even gravitational wave physicists join the dialogue, as some ejection events may produce ripples in spacetime detectable with future instruments. New telescopes and surveys on the horizon promise to expand our horizons. The Vera Rubin Observatory's Deep Time Domain Survey will find transient events and faint high-speed stars. Space-based missions, like Euclid and the Roman Space Telescope, will provide exquisite astrometry and photometry. Together, they will allow us to identify hypervelocity stars, not only in our own galaxy, but in nearby galaxies, opening the door to comparative studies of galactic centers. These wandering suns also serve as bridges between fields. Their velocities record interactions with black holes. Their chemical compositions reveal the environments in which they formed. Their trajectories depend on the halo they traverse. By studying them, we link star formation to black hole dynamics and galaxy evolution. Each piece of information connects microcosmic processes with the macrocosmic architecture of the universe. Speculation invites us to look further. Could there be hypervelocity neutrinos produced in core collapse supernovae, or hyperfast fragments of planets stripped from their stars? Might cosmic rays include contributions from shattered worlds, accelerated in the gravitational melee near black holes? These questions hover on the frontier, hinting at phenomena yet unobserved. The universe remains full of surprises. It is humbling to realize that even as we chase these stars with our telescopes, we ourselves are riding on a planet hurtling through space. Our solar system arcs around the galaxy at hundreds of kilometers per second, and the galaxy itself drifts through the cosmic web. In this sense, there is no fixed point. There are only relative motions at different scales. The hypervelocity stars are exceptional not because they move and we do not, but because their motions break the bonds that hold most stars in place. Recognizing this continuity between their journeys and ours deepens our connection to the universe. As we close this section, it is clear that we have only begun to explore the terrain. The tales of hypervelocity stars span physics, astronomy, and philosophy, and their full implications are still unfolding. In the chapters ahead, we will turn our attention to other facets of this story. The journey continues, and the mysteries deepen. One might wonder whether these speeds tell us anything about the expansion of the universe. The answer lies in distinguishing between motion relative to the galaxy and the overall cosmic flow. Hypervelocity stars are propelled by gravitational interactions within the Milky Way and its neighbours. Their velocities are measured relative to the galactic rest frame, while cosmic expansion tugs galaxies apart on the largest scales. Its effect on the motions of individual stars within a galaxy is negligible. This contrast highlights the many layers of motion that overlay one another in the universe. Hypervelocity stars also carry memories of their birth environments. The chemical fingerprints in their atmospheres reveal the composition of the gas clouds from which they formed. When a star is ejected from the galactic center, or a dense cluster, it preserves information about conditions in those extreme environments. By analyzing their abundances, astronomers can reconstruct aspects of star formation history near the galaxy's core. In this way, runaway stars become messengers from regions otherwise difficult to study. As these stars depart, they carry more than just memories. They carry material. Stellar winds, and eventually, supernova explosions will enrich the space they traverse with heavy elements. If a hypervelocity star lives long enough to explode outside the galaxy, its metals will be dispersed into the intergalactic medium. Over cosmic time, such outflows contribute to the enrichment of diffuse gas between galaxies. Though the contribution may be small, it is a reminder that processes on the scale of individual stars can influence the broader chemical evolution of the cosmos. The story of hypervelocity stars is thus both singular and universal. Each star's journey is a unique response to a specific encounter. Yet together, they illuminate themes that recur throughout astrophysics: the transfer of energy, the interplay of gravity and motion, and the flow of matter. By following these celestial messengers, we see how local interactions can have far-reaching consequences, and in contemplating their travels, we find ourselves connected to a wider tapestry of cosmic change. Comets, those icy wanderers, provide another glimpse into cosmic motion. Some follow short, periodic paths, returning every few decades, while others plunge in from the distant Oort cloud on journeys lasting hundreds of thousands of years. Their elongated orbits remind us that gravity governs more than just planets and stars. It orchestrates the motion of small bodies across vast expanses. On million-year timescales, our solar system itself drifts through different regions of interstellar space. It presently moves through a diffuse collection of gas known as the local interstellar cloud. In the past, it has traversed bubbles cleared by supernovae, or denser clouds laden with dust. These passages influence the cosmic rays that bombard Earth and may subtly affect the climate over geological eras. If we imagine the galaxy as a river, the stars are boats carried along by the current. They drift at different speeds depending on their distance from the center, but they are all part of the same flow. Occasionally, eddies form where gravitational perturbations create local turbulence. Within this river, hypervelocity stars are the rare logs shot out of the riverbed, skipping across the surface and heading for the bank. Galactic motion is also shaped by interactions with other galaxies. The Milky Way is currently in the process of absorbing smaller companions. As these dwarf galaxies fall in, their stars are stretched into streams that wrap around the main galaxy. These tidal streams are relics of ancient mergers, revealing how the Milky Way grew over time. The stars in these streams move coherently, maintaining their identity amid the larger flow. Some stars in the halo move in retrograde orbits, traveling opposite to the general rotation of the disk. These stars likely originated in dwarf galaxies that merged with the Milky Way long ago. Their unusual motions are fossils of those events. By studying them, astronomers can reconstruct the history of cosmic cannibalism that built the galaxy. At the heart of every motion in the universe lies the conservation of momentum. From the expanding fabric of space that began in the Big Bang to the orbit of a moon around its planet, momentum governs how objects move. The cosmic expansion itself is a kind of motion, carrying galaxies apart, even as gravity binds them into clusters. Within stars, movement is incessant. Hot plasma rises and falls in convective currents, transporting energy from the core to the surface. These flows generate magnetic fields that can twist and snap, producing flares and spots. Even within the apparent serenity of a sun-like star, turbulence reigns. Motion pervades every scale. Gravity's influence diminishes with distance. Stars far from the galactic center feel a weaker pull and thus move more slowly. This gradient in gravitational strength shapes the rotation curve of the Milky Way. The unexpected flatness of that curve revealed the presence of dark matter. Without this unseen mass, the outer stars would not be bound, and the spiral would fly apart. The principles that describe these motions are elegantly simple. Newton's laws capture the balance between force and motion, while Einstein's general relativity extends these ideas to include the curvature of spacetime. Though expressed with equations, the essence is straightforward. Masses attract, motion resists change, and the interplay between the two creates orbits and trajectories. As we proceed, keep in mind that the extraordinary events we will explore are not separate from this cosmic symphony. They are notes in a long, slow melody that has been playing for billions of years. Understanding the background music allows us to appreciate when a sudden crescendo occurs. Hypervelocity stars are such crescendos, brief, powerful bursts of motion against a serene backdrop. Although we talk about the Milky Way as a whole, it is helpful to picture its structure and the patterns that maintain its quiet order. Our galaxy is a barred spiral, a flattened disk with a central bar of stars and long, sweeping arms. These arms are not solid objects, but density waves that move through the disk like slow ripples through water. Stars drift in and out of them, spending only a fraction of their orbits within their bright lanes. Gravity governs every component of this structure. Near the center lies a bulge of old stars, orbiting in random directions, but held close by a deep gravitational well. Surrounding the bulge is the bar, a cigar-shaped concentration of stars that rotates slowly. Beyond the bar, the spiral arms wind outward, each marked by newborn stars and glowing clouds. The whole is embedded in a halo of dark matter that extends far beyond the visible disk. Different kinds of stars share this gravitational framework. Massive blue stars burn brightly and live short lives, tracing arcs through the spiral arms. Modest yellow stars, like our Sun, complete long, stable orbits, weaving through the arms over billions of years. Ancient red dwarfs follow similar paths, hugging the disk or drifting slightly above and below it. The variety of stellar journeys is unified by the overall gravitational potential. From above, the Milky Way would look like a pinwheel with 4 major arms and several spurs. Our Sun sits in a small spur called the Orion arm, between the larger Sagittarius and Perseus arms. The spiral pattern rotates slowly compared with the individual stars. So as the Sun circles the galaxy, it moves in and out of these arms. Each passage can trigger waves of star formation, but it does not disturb the overall order. Closer to the center, in the crowded bulge, stars orbit in more elliptical and inclined paths. Collisions are rare despite the density, because the vast distances between stars make direct encounters unlikely. The bulge contributes to the gravitational pull that keeps the disk intact. Even here, the average motions are predictable, maintaining a balance between gravitational attraction and orbital momentum. In the outer disk, stars move a bit more slowly, and the density of material is lower. This region contains gas and dust that warp the disk slightly, giving it a gentle curve like the brim of a hat. Despite these variations, the gravitational grip of the galaxy extends far beyond the visible edge, binding stars thousands of light years away. They too orbit calmly, swept along by the unseen dark matter halo. Spiral arms are not static structures. They are created by resonances within the disk, where the orbital period of stars matches the pattern speed of the density wave. As a star encounters an arm, it slows slightly, adding its mass to the arm's brightness. After passing through, it speeds up again. This interaction is gentle. It does not fling the star out of the galaxy. Instead, it sustains the spiral pattern and fosters the birth of new stars. Within these arms, open clusters form when dense clumps of gas collapse. Hundreds of stars may emerge together, sharing similar orbits. Over time, interactions within the cluster and with passing clouds cause the cluster to disperse. The stars then join the general stellar population, continuing to orbit calmly. This constant cycle of cluster formation and dissolution contributes to the dynamic equilibrium of the disk. The Milky Way's gravitational potential encourages stars to follow nearly circular paths. Small deviations in speed or direction lead to gentle oscillations rather than dramatic departures. These oscillations contribute to the thickness of the disk. They are like ripples on a pond, adding texture without disturbing the overall surface. Only significant perturbations can alter these paths drastically. Such perturbations can come from passing galaxies or massive molecular clouds. When a dwarf galaxy like Sagittarius brushes past the Milky Way, it can tug on stars, altering their orbits slightly. These interactions may create streams of stars, but rarely accelerate them to escape speeds. The quiet order is resilient. Gravity redistributes energy in a way that preserves the overall structure. An analogy to a river helps illustrate this stability. Stars flow through the gravitational potential like water through a valley. The valley guides the water, and the water's speed depends on the slope. Small rocks cause ripples, but do not change the river's course. Only a significant disturbance, like an earthquake, could divert the flow completely. In the galaxy, only extraordinary events can hurl a star out of its orbit. Observations from missions like Gaia have given us a detailed map of these motions. By measuring the positions and proper motions of over 1 billion stars, astronomers have charted the swirling patterns of the disk. They see streams of stars moving together, remnants of ancient clusters and dwarf galaxy mergers. They also detect stars with high peculiar velocities, the first hints of disruptions in the quiet order. Despite the complexity of individual motions, the Milky Way's gravitational field acts as a stabilizing force. Through countless interactions and passages, energy is shared and redistributed. This process smooths out extreme deviations. Over time, stars settle into orbits appropriate to their energy and angular momentum. The result is a stable disk with well-defined structures. Across billions of years, stars will migrate within the disk. They may drift outward or inward due to subtle gravitational torques. They may cross spiral arms and experience bursts of radiation and gravitational perturbations. Yet, because they remain bound, they will continue to orbit. Their migration contributes to mixing the chemical elements and redistributing energy throughout the galaxy. The calm environment provided by this order has allowed planetary systems to form and evolve. Our Sun has spent its life in a relatively quiet region, away from the disruptive gravitational tides near the center or the sparse outskirts. This stability likely played a role in the emergence of complex life. It underscores how fortunate we are to reside in a galaxy that maintains such gentle order over billions of years. Because this quiet order is so pervasive, anything that breaks it is noteworthy. A star traveling at twice the typical orbital speed will not go unnoticed. When astronomers find such a star, they know something unusual has occurred. It may have been flung by a supernova or tossed by a gravitational slingshot. The event that launched it stands out against the calm background. In the next chapter, we will examine the circumstances under which this orderly pattern can be disrupted. We will see how interactions within crowded clusters or the violent death of a star can impart enough energy to send a companion racing through the galaxy. These rare events are the seeds of chaos in an otherwise orderly cosmos. For now, imagine the Milky Way as a cosmic sea. Waves of stars flow around the center. Currents of gas swirl along the arms, and islands of clusters drift slowly apart. The sea is vast, deep, and surprisingly tranquil. On this sea, occasional storms arise. When they do, they leave ripples that propagate far and wide, carrying news of the disturbance. The quiet order of the galaxy is the backdrop for our tale. Without it, the extraordinary would seem ordinary. By understanding the baseline, we are better prepared to appreciate the anomalies. And it is these anomalies, the runaway and hypervelocity stars, that provide clues to hidden forces and unseen companions lurking within the Milky Way. The disk of the Milky Way is not a uniform sheet. It thickens toward the center and flares at the edges. This flaring reflects the distribution of stars and gas, with younger stars and gas concentrated in the thin disk, and older stars spread out in a thicker component. The thickness adds dimension to the quiet order, creating layers of motion. The central bar influences orbits throughout the inner galaxy. Stars near the bar can become trapped in resonances where their orbital periods match the pattern speed of the bar. In these resonant regions, stars follow elongated paths aligned with the bar. This resonance structure is part of the orderly architecture, guiding stars without causing chaos. Gas and dust in the interstellar medium follow the stars, but also respond to pressure and shock waves. As spiral arms rotate, they act like traffic jams on a highway, compressing gas and triggering star formation. Behind each spiral arm, newborn stars illuminate the gas, marking the arm's location. Yet the gas flows through, continuing its journey around the galaxy. Beyond the disk lies the halo, a spherical region populated by old stars and globular clusters. These clusters are tightly bound groups of hundreds of thousands of stars, relics of the early galaxy. They orbit slowly and in various directions, contributing to the overall gravitational field. Their presence does not disturb the disk. Instead, they are part of the broader quiet order. Globular clusters themselves have stories to tell. Some may have been captured from dwarf galaxies that merged with the Milky Way. Their orbits and chemical compositions help astronomers trace the accretion history of the galaxy. Despite their independent trajectories, they remain gravitationally bound, adding their mass to the halo and helping stabilize the galaxy's rotation. The dark matter halo surrounding the visible galaxy is thought to be roughly spherical. It extends far beyond the disk and bulge, dominating the mass budget. This unseen component shapes the rotation curve of the galaxy, keeping the outer stars in their orbits. Without dark matter, the quiet order would not exist. The galaxy would be unable to hold on to its stars. The disk is slightly warped, bending upward on one side and downward on the other. This warp may result from interactions with satellite galaxies or a misalignment with the dark matter halo. Despite the warp, stars follow its contours, maintaining their orderly motion. It is as if the disk were a flexible record, gently rippled but still spinning smoothly. Radial migration is another process within the disk. Over time, stars can move inward or outward due to interactions with spiral arms and bar resonances. This migration helps mix chemical elements, smoothing out abundance gradients. It does not disrupt the overall order. Instead, it contributes to the galaxy's long-term evolution by slowly stirring the stellar population. Chemical gradients offer another perspective on order. Stars closer to the center generally have higher metallicities because the star formation rate has been higher there. As stars migrate, they carry their chemical signatures with them. Over billions of years, this mixing blurs the gradient, yet the underlying structure remains. The galaxy changes slowly, maintaining balance while allowing for subtle evolution. All these processes, flaring, resonances, gas flows, halo motions, dark matter support, warps, migration, and chemical mixing, combine to make the Milky Way a living system. It evolves on timescales far beyond human lifetimes. Within this grand equilibrium, extraordinary events like hypervelocity, star ejections are rare. Their rarity is what makes them so informative when they occur. There are moments when the galaxy's orderly dance is interrupted. A star that has followed a stable orbit for millions of years can suddenly be thrust onto a new path. In these rare cases, the grip of gravity is broken and the star is free to roam. The causes of such disruptions lie in the complex interactions between stars, particularly in binaries and clusters, and in the violent deaths of massive suns. Many stars are born in pairs or multiple systems, orbiting a common center of mass. These intimate relationships are common, especially among massive stars. As the stars evolve, their fates become intertwined. If one of the stars reaches the end of its life and explodes as a supernova, the sudden loss of mass can unbind the pair. The companion, no longer tethered, flies off with its previous orbital velocity, becoming a runaway. This mechanism is known as the binary supernova scenario. A massive star exhausts its nuclear fuel, its core collapses, and its outer layers are blasted away. The explosion may leave behind a neutron star or black hole. The remaining companion was previously orbiting at a high speed to remain bound. When the primary star's gravity vanishes, the companion continues in a straight line, depending on the details of the orbit and the kick from the explosion. Its speed can be tens or even hundreds of kilometers per second, relative to the local medium. Many runaway stars known today are of spectral types O and B. They are hot, massive, and short-lived. Their high velocities make them stand out when astronomers chart the motions of stars near the Sun. These runaways are often found far from their likely birthplaces in young clusters, testifying to past events that sent them hurtling away. Most continue to orbit the Milky Way, albeit on paths that take them to unusual locations in the halo. Another pathway to becoming a runaway involves dynamical ejections within crowded clusters. In these environments, stars are packed closely enough that gravitational interactions between multiple systems are frequent. When two binaries pass near each other, they can exchange partners or fling one member out entirely. Single stars can also be slingshotted when they encounter a binary. The result is a star with a velocity significantly higher than its neighbours, though typically still bound to the galaxy. Young clusters, particularly those forming massive stars, are fertile grounds for such interactions. The core regions of these clusters contain dozens of massive stars within a few light years, leading to a cosmic game of billiards. Each close approach redistributes energy and momentum. Most stars gain or lose only small amounts of speed. Occasionally, a star is in the right place at the right time to receive a substantial push. It becomes a runaway, leaving the cluster behind. These two mechanisms, binary supernova and dynamical ejection, produce stars that move faster than their peers. Yet their speeds are modest compared with those needed to escape the galaxy. They might reach 100 or 200 kilometers per second, sometimes more. These velocities are enough to carry them hundreds of thousands of light years over millions of years. But gravity ultimately keeps them bound. They remain part of the Milky Way's extended halo. To produce a hypervelocity star, the velocity must be extreme. The star must exceed the escape speed of the galaxy, which near the Sun is around 500 to 600 kilometers per second. Near the center, where gravity is stronger, the escape speed is even higher. Some runaways approach these speeds, but do not surpass them. Only a handful of stars have been observed traveling at velocities high enough to leave the Milky Way entirely. The binary supernova mechanism can occasionally produce higher velocities, especially if the explosion is asymmetric. The companion star may receive an additional kick from the supernova ejector, boosting its speed. In rare cases, this can push the star toward the escape velocity. However, the energies involved are typically not sufficient to propel a star beyond the galaxy's gravitational reach. Something else must provide the extra push. One variant involves a white dwarf accreting material from a companion star. As matter piles onto the white dwarf, a layer of helium builds up. When enough helium has accumulated, it can ignite, triggering a second detonation in the core. The entire white dwarf explodes in a type Ia supernova. The donor star, suddenly deprived of its partner and buffeted by the explosion, is hurled away at high speed. These donor stars are helium-rich and show signs of supernova material in their atmospheres. Astronomers look for chemical fingerprints to identify such scenarios. A runaway star enriched with heavy elements like calcium or iron might have been polluted by supernova ejecta. Its unusual composition would betray a violent past. Combined with its high velocity, this evidence can point to a supernova origin. Observations of such stars help refine models of how supernovae explode and how much energy is transferred to companions. In clusters, gravitational encounters can also be enhanced by the presence of intermediate mass black holes. If a star passes close to such a black hole, it can be accelerated significantly. The gravitational field acts like a slingshot, imparting kinetic energy to the star. For clusters containing black holes of a few thousand solar masses, the speeds achieved can be high, although typically not enough to unbind the star from the galaxy. Still, these interactions add to the diversity of runaway velocities. Some runaway stars have been traced back to clusters in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Clusters like R136 host numerous massive stars, and the interactions within them are intense. When astronomers follow the trajectories of runaways, they sometimes point back to these clusters. This information provides clues about the existence of massive unseen objects within the clusters and about the dynamics of stellar birth environments. At the heart of all these scenarios is the conservation of energy and momentum. When a system loses mass or experiences a gravitational encounter, the energy that once bound the system can be converted into motion. The companion star, or the single star involved, carries away this energy as kinetic energy. The velocity it attains depends on the masses involved and the nature of the interaction. In most cases, the speeds are high, but not enough to escape the Milky Way. These runaways act as messengers. They tell us about the environments in which they formed. A runaway star from a supernova carries information about the mass of the exploding star and the asymmetry of the explosion. A runaway from a cluster informs us about the density of stars and the presence of black holes. By studying the velocities and compositions of runaways, astronomers reconstruct the hidden events that launched them. Yet, despite the violence of these ejections, most stars remain gravitationally bound. The Milky Way's gravity is strong. To leave, a star needs an exceptionally powerful kick. The mechanisms described so far provide high speeds, but rarely enough to overcome the galaxy's grip. Hypervelocity stars require a more dramatic source of energy, one capable of imparting velocities of hundreds or even thousands of kilometers per second. To understand those, we must look to the heart of the galaxy and beyond. The first hints that such extreme speeds existed came from careful measurements of stellar motions. Astronomers surveying the halo of the Milky Way noticed a few stars whose radial velocities were far larger than those of typical halo stars. These objects were moving so quickly that if their distances and motions were correct, they would be unbound. The idea of a star escaping the galaxy was no longer theoretical. Evidence was emerging that it could happen. In 2005, a team analyzing data from a telescope in Arizona reported the discovery of a star racing through the halo at over 1,000 kilometers per second. Its speed was so high that the Milky Way's gravity could not pull it back. This star was the first of its kind, a stellar refugee. Its trajectory pointed roughly away from the center of the galaxy, suggesting that it had been launched from deep within. The discovery ignited curiosity about what powerful engine could have flung it so far and so fast. Subsequent observations confirmed that this was not an isolated case. Astronomers began to find more stars with velocities near or above the escape speed. Each new discovery added nuance to the picture. Some stars were massive and young, others were smaller and older. Their compositions varied. What they shared was a velocity that exceeded what the galaxy's rotation could account for. By the middle of the next decade, a few dozen candidates had been identified, though only about 20 were confirmed beyond doubt. One particularly striking example was found in the southern sky in 2019. This star, designated S5HVS1, was moving at about 1,800 kilometers per second, over 6 million kilometers per hour. It was roughly twice the mass of the Sun and appeared to have been flung from the galactic center around 500 million years ago. Its speed and trajectory were consistent with a close encounter with the supermassive black hole at the galaxy's core. S5-HVS1 became a textbook case of a hypervelocity star. Not all hypervelocity stars are massive. In the early 20s, a group of citizen scientists sifting through data from a space telescope discovered a faint object moving at roughly 1 million miles per hour. This object was much less massive than the Sun, possibly even a brown dwarf. Its chemical composition suggested it was very old, and it was found relatively close to our solar system. The find demonstrated that even low-mass stars or substellar objects can achieve hypervelocity, expanding the diversity of known runaway objects. Another intriguing case involved a small red dwarf star orbiting a planet. The star, located deep in the galactic bulge, was found to be moving at around 540 kilometers per second, just shy of the escape speed near the Sun. Attached to it was a planet roughly 30 times the mass of Earth. The discovery showed that ejected stars might carry planets with them, suggesting that the mechanism launching them did not necessarily strip away their companions. This planetary hitchhiker widened our understanding of what hypervelocity systems could look like. Some hypervelocity candidates did not trace their paths back to the galactic center at all. One object, known as Lamost HVS1, appeared to originate from the Milky Way's disk rather than the central black hole. Its trajectory implied that it had been ejected from a region rich in massive stars, possibly after a complex interaction with multiple stars, or an intermediate mass black hole. This case reminded astronomers that more than one pathway could lead to extreme speeds. To determine the origins of these stars, astronomers rely on precise astrometry and spectroscopy. Missions like Gaia provide accurate positions and motions for billions of stars. When combined with measurements of radial velocity from ground-based telescopes, these data allow astronomers to reconstruct the three-dimensional motions of hypervelocity stars. By projecting their orbits backward in time, they can see where they likely came from. In many cases, the paths point toward the galactic center, or toward clusters in the Large Magellanic Cloud. The chemical compositions of hypervelocity stars also offer clues. Stars born near the center of the Milky Way often have different metallicities than those born in the outer disk or in satellite galaxies. If a hypervelocity star has a composition matching the Large Magellanic Cloud, it suggests an origin there. If its chemical fingerprints match those of the inner Milky Way, the galactic center becomes the likely launch site. Such analyses have revealed that roughly half of the known hypervelocity stars may have come from our neighbor galaxy. The diversity of hypervelocity stars is striking. Some are blue and massive, others are yellow and sun-like, and a few are faint, low-mass dwarfs. Some show signs of having been part of a binary system, others do not. Their atmospheres range from hydrogen-rich to helium-rich. This variety indicates that multiple ejection mechanisms are at work. It also means that each star carries unique information about the environment it left behind. Despite their variety, hypervelocity stars share one characteristic. They are rare. Out of the hundreds of billions of stars in the Milky Way, only a few dozen have been identified as hypervelocity. Finding them is like finding a handful of needles in a haystack the size of a continent. Surveys like Gaia are essential for this work, but even with such powerful tools, it takes careful analysis to distinguish a true hypervelocity star from an ordinary fast mover. The process of confirming a hypervelocity star involves several steps. First, the star's radial velocity must be measured accurately. Next, its proper motion must be known to determine its tangential speed. The distance to the star must also be measured or estimated. With these three ingredients, astronomers can calculate the total space velocity. They then compare this with the local escape speed. If the star exceeds that speed and its trajectory is consistent with an origin near a known launch site, it is classified as hypervelocity. Once launched, a hypervelocity star is destined to leave the galaxy. It will travel through intergalactic space, cooling and dimming as it goes. For billions of years, it will wander the dark between galaxies, carrying with it the chemical signature of its origin. We will not see these stars again. Their passage is fleeting on cosmic timescales, yet their existence tells us that the Milky Way is not a closed system. It loses stars through rare but powerful events. Each discovery leads to new questions. How common are intermediate mass black holes that can sling stars from clusters? What fraction of hypervelocity stars carry planets? Can a supernova impart enough speed to fully unbind a star? Do all galaxies have populations of hypervelocity stars? The answers have implications for our understanding of black hole populations, stellar evolution, and the dynamics of galaxies. The first hypervelocity star hinted at one mechanism, but subsequent discoveries have revealed complexity. Some stars clearly come from the galactic center, supporting the idea that interactions with the central black hole can fling stars. Others point to dense clusters in the Large Magellanic Cloud, implying that a massive black hole lurks there as well. A few defy easy classification, hinting at yet unknown processes. The pattern that seemed simple at first has become a rich tapestry. The search for hypervelocity stars continues. Future surveys will extend to fainter magnitudes and wider areas of the sky. Citizen science projects, where volunteers scan data for unusual motions, will help identify candidates. As we find more, we will refine our theories and perhaps discover new ejection mechanisms. Each new star will be a piece of a puzzle that spans the Milky Way and its neighbors. As we move to the next section, we will explore how the mystery of these stars deepened as astronomers sought to explain their origins. The discovery phase was only the beginning. What began as an anomaly has become a field of study. The challenge now is to connect each hypervelocity star to a source and to understand the cosmic events that created them. In the process, we will learn more about the hidden heart of the galaxy and the forces that shape it. With the identification of more than a handful of hypervelocity stars, astronomers realized that they were dealing with a distinct phenomenon. The velocities involved were too great to arise from ordinary stellar interactions. Moreover, the stars seemed to trace their paths back to specific regions. In many cases, the trajectories converged on the central few parsecs of the Milky Way. This pointed to a powerful accelerator residing there. At the center of our galaxy lies Sagittarius, a star, a supermassive black hole with a mass of about 4 million suns. Surrounding it are dense clusters of stars and clouds of gas. In the late 1980s, theorist Jack Hills proposed that when a binary star ventured close to such a black hole, tidal forces could rip the pair apart. One star would be captured into a tight orbit around the black hole, while the other would be flung outward at high speed. This simple yet dramatic mechanism became known as the Hills mechanism. In this scenario, the ejected star gains energy at the expense of the captured star. As the binary is pulled apart, gravitational potential energy is converted into kinetic energy. The captured star loses energy and ends up bound to the black hole, perhaps orbiting it on a short period. The other star is accelerated to a velocity that can exceed the escape speed of the galaxy. The stronger the tidal interaction, the larger the kick imparted. This process can produce velocities of thousands of kilometers per second. Observing hypervelocity stars provides indirect evidence for the existence and properties of the black hole at the center. We cannot see Sagittarius A star directly, but we can see its gravitational influence. The orbits of stars around it have been measured, confirming its mass. Hypervelocity stars ejected by it carry away information about its past interactions. They are like projectiles fired from a hidden cannon, telling us about the energy of the gunpowder and the direction of aim. By analyzing the trajectories of hypervelocity stars, astronomers have found that roughly half of those known originate from the Milky Way's center. Their paths point back to a region only a few light-years across. This confirmation of the Hills mechanism is one of the triumphs of modern galactic dynamics. It shows that the central black hole is not merely a passive sink of matter, but an active participant in shaping the stellar population of the galaxy's halo. Yet not all hypervelocity stars come from this region. Several have trajectories that intersect with the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. When their motions are traced back, they appear to have been launched from within the LMC tens of millions of years ago. To explain this, astronomers proposed that the LMC harbors its own massive black hole, albeit smaller than Sagittarius A star. Estimates based on the stellar velocities suggest a mass of about 600,000 suns, consistent with the LMC's size. If the LMC does contain such a black hole, it means that other galaxies, even small ones, can produce hypervelocity stars. The Milky Way may be receiving these refugees as they pass through. The fact that roughly half of the known hypervelocity stars can be traced to the LMC indicates that this neighbor plays a significant role in populating our halo with high-speed stars. This realization broadened the scope of the hypervelocity star phenomenon beyond our own galaxy. Despite these successes, the hypervelocity star story is not fully resolved. The speeds predicted by the Hill's mechanism can be extremely high, yet most observed hypervelocity stars have velocities below 1,000 kilometers per second. There is a sharp cutoff around 700 kilometers per second. This discrepancy suggests that something moderates the energy transfer, or that we have not yet observed the fastest stars. The absence of extremely high-speed stars was puzzling. One proposed explanation involves the presence of an intermediate mass black hole near Sagittarius A star at some point in the past. If the supermassive black hole had a companion with a mass of a few tens of thousands of suns, their combined gravitational field could limit the velocities imparted to ejected stars. The companion would act as a gravitational kicker, redirecting the escaping stars and capping their speeds. Such a scenario would also clear out the region around Sagittarius A star, explaining why there are few young stars in certain orbits today. Another mystery arises from the lack of surviving companions near the galactic center. If binary interactions are producing hypervelocity stars, we should find their companions orbiting Sagittarius A star in close, tight orbits. Yet surveys have not found as many such companions as expected. This absence hints that the binaries interacting with the black hole may be disrupted entirely, or that they are sufficiently rare. Understanding why companions are missing is an active area of research. Some hypervelocity stars, like HE0437-5439, present additional puzzles. This star is massive and appears young based on its surface temperature and luminosity. Yet its position far in the halo implies that it has been traveling for 100 million years, longer than its apparent age. To reconcile this, astronomers suggest that it is a blue straggler, a star rejuvenated by the merger of two smaller stars in a triple system. In this scenario, a triple star approaches the black hole. One component is captured, and the other two merge and are ejected. The merged star appears young, solving the age paradox. The case of Lamost HVS. One points toward another possibility: intermediate mass black holes within the Milky Way's disk. This star's trajectory does not lead back to Sagittarius A star, but to a region rich in young, massive stars. A black hole with a mass of a few thousand suns in that region could have accelerated the star. If such black holes exist, they may be remnants of clusters or dwarf galaxies that merged with the Milky Way. Their detection through hypervelocity stars would be an indirect yet powerful method of discovery. The double detonation supernova scenario provides another route to hypervelocity. In this model, a white dwarf accretes helium from a companion until the helium ignites. The resulting explosion triggers a second detonation in the core, destroying the white dwarf. The companion star, enriched with supernova debris and with its envelope expanded by the blast, is thrown away. Such stars are helium-rich and have unusual chemical compositions. Their velocities can reach the escape speed of the Milky Way. Observations of such stars support this mechanism. Each ejection scenario highlights different aspects of astrophysics. The Hills mechanism showcases the role of supermassive black holes in stellar dynamics. The supernova scenarios reveal the physics of stellar explosions and binary evolution. Dynamical interactions in clusters emphasize the importance of stellar density and intermediate mass black holes. Hypervelocity stars thus serve as probes of phenomena that are otherwise difficult to observe directly. Long before the first such star was found, astronomers speculated that extreme encounters might fling stars outward. The idea had to compete with prevailing views of an orderly galaxy, so it remained more of a curiosity than a pressing question. Pioneering thinkers imagined dense clusters and black holes acting as slingshots, but without observational evidence, the concept floated like a myth on the margins of astrophysics. The theoretical foundation for these dramatic ejections was laid in the late 1980s by physicist Jack Hills. He calculated that a binary star wandering too close to a supermassive black hole would be torn apart, with one star captured and the other shot out at tremendous speed. His work predicted that some stars could reach velocities high enough to escape the Milky Way. For years, this Hills mechanism was little more than a footnote in papers about galactic centers. For decades, no one had the data to test Hills's prediction. The instruments of the time could not easily measure the full three-dimensional motion of distant stars, especially those faint enough to be hidden among the halo's sparse population. Observers focused on more accessible questions. The possibility of stars leaving the galaxy remained a theoretical intrigue without an observational anchor. That changed with advances in spectroscopy and astrometry at the turn of the millennium. By measuring the Doppler shift of a star's light, astronomers could determine how fast it was moving toward or away from us. When combined with precise measurements of position and proper motion, this revealed the star's path through space. A star with an unusually high velocity would stand out like a streak in a long exposure photograph. The team that discovered the first hypervelocity star in 2005 initially questioned their own results. They checked the instrument, remeasured the spectrum, and considered alternative explanations, like binary motion or pulsation. Only after careful analysis did they accept that the star's velocity was real and unbound. Their discovery transformed a speculative idea into a concrete phenomenon, opening a door to new questions. The term hypervelocity was coined to distinguish these extraordinary objects from ordinary runaways. The word conveys a sense of something beyond the typical, a movement so swift that it crosses the boundary between what is bound and unbound. Naming the phenomenon gave researchers a common language and helped galvanize the search for additional examples, turning a single discovery into a burgeoning field. As the sample of hypervelocity stars grows, astronomers refine the criteria for classifying them. Not every fast star is hypervelocity. A star might be moving at a few hundred kilometers per second relative to its neighbors, but still be bound. The distinction depends on the local escape speed and the star's trajectory. In this way, hypervelocity stars are the extreme tail of the runaway population. Their rarity underscores the extraordinary circumstances required to create them. The birth of this mystery has transformed hypervelocity stars from curiosities into tools. By analyzing their velocities, trajectories, and compositions, scientists measure the gravitational potential of the Milky Way and its satellites. They test theories of binary interaction, supernova physics, and black hole demographics. These stars are cosmic laboratories carrying information from environments otherwise inaccessible. As this chapter ends, we acknowledge how a small number of stars have opened windows into the most extreme environments in our galaxy and beyond. The questions raised by their existence have sparked new theoretical work and prompted more detailed observations. In the next chapter, we will accompany astronomers as they continue the search for clues, devise new surveys, and refine models. The story of hypervelocity stars is still unfolding, and its mysteries are far from solved. To unravel these mysteries, astronomers are casting a wide net. The first step is to find more hypervelocity stars. Missions such as Gaia continue to map the positions and motions of billions of stars with unprecedented precision. By comparing current positions with past ones, astronomers can calculate proper motions. When a star shows both a high proper motion and a high radial velocity, it becomes a candidate. Follow-up spectroscopic observations then determine its full three-dimensional velocity. In the coming years, the Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, will deepen this search. The LSST will take repeated images of the entire southern sky, capturing changes in brightness and position over time. Faint, fast-moving stars that might escape other surveys will be noticed. The cadence of observations will help distinguish hypervelocity stars from other transient phenomena, such as asteroids or variable stars. The LSST's deep reach will extend the hypervelocity census into the outer halo. The Nancy Grace Roman Space Telescope will add a different perspective. Designed primarily for wide-field infrared imaging and microlensing searches, it will monitor dense star fields toward the galactic bulge. In doing so, it will collect precise astrometry and photometry for millions of stars. Hypervelocity stars passing through these fields may be detected. If a hypervelocity star hosts a planet, a microlensing event could reveal it. Thus, Roman may find both the stars and their companions. Citizen scientists also play a role in the search. Projects that allow volunteers to inspect data for unusual motions have already borne fruit. The low-mass hypervelocity object discovered in recent years was identified by an enthusiastic amateur who noticed its unusual speed in archival data. Such collaborations broaden the pool of eyes looking for rare phenomena. They also engage the public in the process of discovery, turning the study of hypervelocity stars into a community effort. The search for clues to these extraordinary events begins at the very heart of the Milky Way, the environment around Sagittarius. A star is chaotic, with stars orbiting at breakneck speeds and clouds of gas swirling inwards. Observing this region requires infrared telescopes to peer through dust and adaptive optics to sharpen images. The data gleaned from this crowded domain help constrain the number of binaries and the frequency of close encounters. Detecting a hypervelocity star requires more than a single velocity measurement. Astronomers must measure the component of motion across the sky with extraordinary precision. Instruments like Gaia have made this possible by tracking tiny shifts in a star's position over years. Even a motion of a few milliseconds per year can translate into hundreds of kilometers per second when the star is thousands of light years away. One of the biggest uncertainties in assessing whether a star is unbound is the distance to the star. Parallax measurements provide a direct method, but for very distant or faint stars, the uncertainties are large. An overestimation of distance can artificially inflate the computed velocity. Careful statistical methods and cross-checks with independent distance indicators are therefore essential in confirming hypervelocity status. Improved astrometry has allowed astronomers to reconstruct the past orbits of candidate stars by integrating their motions backward in time within a model of the Milky Way's gravitational field. They can determine where the star likely originated. If the trajectory converges near the galactic center or a known cluster, this strengthens the case for a specific ejection mechanism. If it diverges into the disk, it hints at other origins. Simulations play a guiding role in this detective work. By modeling millions of binary encounters with a supermassive black hole, researchers generate a distribution of ejected velocities and trajectories. They then compare these patterns with observations to see if the real stars match the predicted populations. Mismatches lead to refinements in the models, such as adding a second black hole or varying the distribution of binary separations. As technology advances, the boundary between observation and simulation grows ever thinner. Data from Gaia feed directly into simulations that predict future detections, and simulation outcomes inform the design of surveys. The interplay between real and virtual stars creates a feedback loop that accelerates discovery. In this way, the search for clues becomes a collaborative dance between telescopes, computers, and human curiosity. The search extends beyond the Milky Way. If other galaxies host hypervelocity stars, they could eventually cross intergalactic space. Detecting them would be challenging because of their faintness and distance. However, with sensitive instruments and clever techniques, astronomers hope to identify hypervelocity stars in neighboring galaxies like Andromeda. Comparing their properties with those in our galaxy will provide insight into the universality of the ejection mechanisms. Theoretical work complements observational searches. Computer simulations model encounters between binaries and black holes, interactions within clusters, and the aftermath of supernovae. N-body simulations can track millions of particles, revealing how often hypervelocity stars should be produced and at what speeds. These models test various assumptions: the masses of black holes, the distribution of binaries, and the presence of intermediate mass black holes. They help interpret the limited sample we observe. Observations also focus on the captured companions. If a binary interacts with a supermassive black hole, one star remains behind, orbiting close to the black hole. These stars, known as S stars, have been observed near Sagittarius A star. By studying their orbits, astronomers can infer whether they could be remnants of hypervelocity ejections. Matching an S star to an ejected counterpart would be a triumph, linking two sides of a cosmic encounter. Another avenue of research seeks intermediate mass black holes within star clusters. Such black holes would leave signatures in the motions of cluster stars and in the distribution of stellar velocities. Hypervelocity stars pointing back to a cluster provide indirect evidence. Direct detection might come from gravitational waves when such a black hole merges with another, or from high-energy emissions if it accretes gas. Combining these clues could confirm the existence of these elusive objects. The chemical analysis of hypervelocity stars continues to refine our understanding. High-resolution spectroscopy reveals the abundances of elements on their surfaces. Stars polluted by supernovae will show enhanced heavy elements. Stars born near the galactic center may have different metallicities compared with those from the outer disk or dwarf galaxies. Such chemical fingerprints act as passports, allowing astronomers to trace a star's origin and the processes it has experienced. The discovery of a planet around a high-velocity star prompts questions about planet survival. How can a planetary system remain intact after a violent ejection? Simulations suggest that if the acceleration is gradual, a planet in a close orbit may remain bound. More distant planets may be stripped away. Observing more hypervelocity stars with planets will test these ideas. It also raises the possibility of rogue planets ejected without their stars, wandering the galaxy or intergalactic space. The apparent absence of stars, with velocities above a certain threshold, demands explanation. Is it due to observational bias, where the fastest stars are too faint to detect? Or does it reflect a physical limit imposed by the ejection mechanisms? Models with binary black holes or additional gravitational interactions can produce a velocity cutoff. Continued observations will help distinguish between these possibilities. If extremely high velocity stars are found, theories will need to adapt. One might wonder whether hypervelocity stars slow down as they travel through the halo. In principle, passing through dark matter and sparse gas could create a drag, reducing their speed. In practice, the densities are so low that the effect is negligible. A star traveling at 1,000 kilometers per second will maintain its speed for billions of years. Thus, hypervelocity stars provide clean probes of the halo's gravitational potential without significant interference. By monitoring the orbits of the so-called S-stars around Sagittarius A star, astronomers test general relativity in ways that complement hypervelocity studies. The S-stars whip around the black hole in orbits that precess and redshift as predicted by Einstein's theory. If some of these stars are the captured companions of hypervelocity ejections, linking the two populations could unify observations of extreme gravity and extreme motion. Hypervelocity trajectories also offer a means to map the distribution of dark matter. As these stars traverse the halo, they feel the cumulative pull of visible and invisible mass. Small deviations from predicted paths may reveal clumps of dark matter or the presence of subhalos. Each hypervelocity star becomes a test mass probing the unseen structure of the galaxy. In the coming decades, gravitational wave detectors may detect ripples from the same encounters that launch hypervelocity stars. A close pass of a compact binary near the central black hole could emit a burst of gravitational waves, followed by the ejection of one member at hypervelocity. Observing both the waves and the star would provide a multi-messenger view of a single dramatic event. Hypervelocity stars can, in principle, cross the vast distances between galaxies. A star flung from the Milky Way's center at several thousand kilometers per second would travel 1 million light-years in 1 billion years. If similar stars escape other galaxies, they could populate intergalactic space with faint, fast wanderers carrying the chemical signatures of their origins. Compact remnants, white dwarfs or neutron stars, might be ejected at even higher speeds. A tight binary containing a white dwarf and a massive companion could, after a supernova, hurl the remnant away at a significant fraction of the speed of light. Such hypervelocity remnants would be difficult to detect, but they could appear as isolated sources of high-energy radiation moving through the halo. The notion that planets might survive these violent ejections invites contemplation. A planet clinging to a star, as it is flung from the galaxy, would experience an endless night sky filled with unfamiliar constellations. Though purely speculative, the idea of a planetary system riding a hypervelocity trajectory invites questions about the transfer of material, and possibly even life, across cosmic distances. Cultural imaginations are stirred by the image of a star fleeing its home galaxy. In stories and myths, such a traveler could symbolize exile or freedom. The scientific reality is just as poetic. Physical laws allow for escape, and occasionally a cosmic traveler takes that path. Hypervelocity stars remind us that motion can lead to separation on the grandest scales. These stars also highlight the limits of gravity's grip. Within any bound system, there exists a threshold beyond which an object will not return. By studying stars that cross this boundary, we deepen our understanding of gravitational binding, whether in galaxies, clusters, or planetary systems. The lessons apply across scales, revealing common threads in cosmic structures. As the catalogue of hypervelocity stars grows, distinctions will sharpen between truly unbound travelers and those on long, eccentric, yet bound orbits. Refined models of the Milky Way's mass distribution will provide better escape speed estimates at different radii. With improved precision, we may even discover new subclasses, stars that hover near the threshold, neither fully bound nor entirely free. Ultimately, the study of hypervelocity stars is about energy and motion. It connects the life cycles of stars with the deep gravitational wells of galaxies, the explosive deaths of massive stars, and the intricate dances of binaries. By tracing these connections, astronomers weave a narrative that unites seemingly disparate phenomena under a single, elegant framework of dynamics. Astronomers also look for stars falling toward the galactic center. If binary interactions eject one star outward, the captured companion should orbit close to the black hole. Over time, gravitational interactions could send it inward, leading to a population of stars plunging into the center. Detecting such inward movers would offer another piece of the puzzle, confirming that ejections occur and revealing the fate of the counterparts left behind. The interplay between observation and theory drives the field forward. Each new hypervelocity star discovered prompts questions that simulations attempt to answer. Each simulation predicts distributions and patterns that observers then seek to confirm or refute. This dialogue refines our understanding, gradually narrowing down the possibilities. It also stimulates improvements in instrumentation and data analysis techniques. Hypervelocity stars touch on fundamental physics. Their trajectories near black holes test the predictions of general relativity in strong gravitational fields. Their existence depends on the gravitational potential of the Milky Way, which is shaped by dark matter. By tracking their motions, astronomers can infer the shape and mass of the dark matter halo. In this way, hypervelocity stars become tools for probing invisible matter and testing gravity itself. As the sample grows, hypervelocity stars will help map the three-dimensional structure of the Milky Way. By knowing their positions and velocities, we can trace the gravitational potential far into the halo. This will refine models of how mass is distributed, which in turn informs our understanding of the galaxy's formation and evolution. Hypervelocity stars are like test particles in an experiment, revealing the shape of the potential they move through. The search for clues is ongoing. We are at the beginning of a long journey. Each discovery adds a brushstroke to the portrait we are painting of our galaxy's hidden structures. As our instruments become more sensitive and our surveys more comprehensive, we will likely find many more hypervelocity stars. Each will bring its own story and contribute to the larger narrative. As this part of our story ends, we pause at a natural break. The questions raised remain open, and the search continues. The journey of hypervelocity stars across the cosmic sea is long, and our exploration of their origins has only just begun. In the chapters yet to come, we will delve deeper into the secrets they carry and the implications they hold for our understanding of the universe. Our journey continues deep within the Milky Way's heart, where a monstrous gravitational engine sits in cosmic silence. It holds 4 million times the mass of our Sun and lies 26,000 light-years away from our quiet solar system. There, swirling gas and dust dance around a void. Yet most of the material never settles, as less than 1% is captured, while the rest is flung back into space. In this environment, we explore how this cosmic anchor quietly shapes the fate of stars. The supermassive black hole's influence reaches far beyond its event horizon, and yet not all is destruction. Astronomers recently detected a young binary star, D9, orbiting close to this dark giant, providing a glimpse into how even fragile systems can survive briefly under intense gravity. At only 2.7 million years old, this pair is a cosmic infant set to merge within 1 million years due to the black hole's pull. This discovery invites us to rethink the interplay between creation and annihilation near galactic centers. When researchers looked deeper, they found hints of gas and dust around D9, suggesting stars can form right next to the supermassive black hole. The presence of such material in the S cluster points to star formation happening in situ, rather than the stars being scattered from elsewhere. These discoveries dispel the long-held notion that extreme gravity sterilizes its surroundings. They offer a picture of resilience and adaptation, where life cycles proceed even under cosmic extremes. D9 resides in a dense hive of stars and dusty objects called the S cluster. Among the cluster's mysteries are the G objects, which look like clouds of gas and dust, yet behave like stars, blurring the line between solid and diffuse states. Astronomers propose that these enigmatic entities could be binary stars that have not yet merged, or the leftover material from stars that already did. This insight hints at a dynamic environment where stellar identities shift over time. Future instruments like gravity, PLUS, and METIS will soon peer more deeply into this region, promising to unravel more secrets. Observers speculate that the detection of planets near the galactic center is just a matter of time, since planets often form around young stars, and the S cluster contains many. Such potential worlds would orbit under the shadow of a supermassive black hole, living in a gravitational landscape unlike any we can imagine. Contemplating such possibilities casts an eerie beauty over the heart of our galaxy. Near the black hole, a population of young massive stars whirls in close orbits, hinting at either in situ formation or migration from afar. When binary stars venture too close, the black hole's tidal forces tear them apart, capturing one companion and ejecting the other into interstellar space. This violent separation is thought to be a primary source of hypervelocity stars racing through the galaxy. Each encounter is a cosmic dance of attraction and repulsion, leaving one partner bound and the other free. The surveys of hypervelocity stars reveal intriguing patterns. Their speeds rarely exceed about 700 kilometers per second. Theory predicts that some should be faster, yet the observed velocities seem capped. Additionally, no captured companions have been found lingering near the black hole, even though they should remain after their partners were flung away. These puzzles challenge our understanding of how energy is partitioned during gravitational interactions. One idea proposes that another massive object once orbited the supermassive black hole, acting like a gravitational goalkeeper. This hypothetical intermediate mass black hole would intercept stars before they approached the main singularity, flinging them away at lower velocities and preventing the most extreme ejections. Such a companion would also disrupt potential captured stars, explaining why none are seen. While unconfirmed, this scenario adds layers to the complex gravitational choreography at the galaxy's heart. Simulations of this goalkeeper scenario predict that only a small fraction, around 2.5%, of ejected stars would exceed 700 kilometers per second. They also suggest that roughly 10% of stars launched from the galactic center should remain as intact binaries. These numbers align with observations, lending credence to the idea that unseen companions or dynamics moderate the violence near the core. It reminds us that even in chaos, patterns can emerge. The Hills mechanism describes this process at a more fundamental level. A binary star system ventures near a supermassive black hole, and the intense gravitational tides rip the pair apart. One star plunges inward, becoming bound to the black hole, while the other is catapulted outward at speeds often exceeding thousands of kilometers per second. This mechanism elegantly explains how otherwise ordinary suns can become cosmic projectiles. It paints the black hole not only as a destroyer, but also as a launcher of wandering stars. A remarkable demonstration of the Hills mechanism came from the hyperfast star known as S5HVS1, which was traced back to the galactic center. Traveling at 6 million kilometers per hour, this star will leave our galaxy entirely, never to return. Astronomers believe its companion was captured by Sagittarius, a star, while S5HVS1 was flung away, making this the first clear observation of the mechanism in action. Such stories show how dynamic the central region truly is. Beyond the galactic core, dense star clusters also host strong gravitational interactions that can propel stars to high velocities. In these clusters, close encounters among stars and compact objects create gravitational slingshots, similar to those near black holes. Sometimes the resulting speeds are enough to overcome the galaxy's pull, launching stars into intergalactic space. These alternative pathways remind us that hypervelocity stars can be born in many cosmic neighborhoods. Astrophysicists recognize several ways to hurl stars outward. The Hills mechanism is the most extreme, accelerating stars to 4,000 kilometers per second if conditions are right. In the binary supernova scenario, one star explodes, suddenly releasing its gravitational grip and leaving the companion to fly off at its orbital speed. Dynamical ejection scenarios involve multi-body interactions in clusters, where close passages between 3 or 4 stars can send one on a high-speed escape. Researchers use Monte Carlo and N-body simulations to study these ejection processes within globular clusters. These models show that clusters can expel stars at speeds up to 2,000 kilometers per second, especially when a cluster contains an intermediate mass black hole. The simulations also reveal that the fastest ejections tend to occur early in a cluster's life, when stellar densities are highest. Over time, as clusters expand and lose mass, fewer stars achieve these extreme speeds. As clusters age, gravitational interactions become less violent, and the production of hypervelocity stars diminishes. This evolutionary pattern means that the current population of ejected stars may carry information about the early history of their clusters. Observing them is like reading the fossil record of a stellar society's youth. It ties dynamic astrophysics to cosmic archaeology. The discovery of star J0731 plus 3717 provides strong evidence for intermediate mass black holes in globular clusters. This star travels at about 550 kilometers per second, 1,000,000 miles per hour, after being ejected from cluster M15. Only a massive compact object could launch a star at this speed, implying the presence of an unseen gravitational slingshot. These findings expand our understanding of black hole populations beyond the galactic center. Tracing J0731 plus 3717 back to its origin shows that it shares the chemical composition and age of M15, confirming it came from that cluster. To achieve such a velocity, A tight binary must have passed within about 1 astronomical unit of an intermediate mass black hole, which then captured one star and flung the other away. This scenario mirrors the Hill's mechanism at a smaller scale, illustrating how universal gravitational slingshots are. Even in remote clusters, massive objects can act as cosmic catapults. The fact that globular clusters can accelerate stars to escape velocities means that not all hypervelocity stars originate from galactic centers. Interactions among stars themselves, especially in crowded environments, can be just as potent. Such multiplicity broadens the search for origins, requiring astronomers to trace trajectories backwards across the Milky Way. Each star's path becomes a clue to its birthplace and the forces that shaped it. Simulations indicate that the earliest phases of globular clusters produce the strongest ejections when the cores are dense and chaotic. During this time, many stars pass close together, creating opportunities for gravitational kicks. Over millions of years, the clusters expand and calm, and the supply of hypervelocity stars dwindles. Observing the distribution of high-speed stars across the galaxy thus offers a time-lapse of cluster life cycles. The young stars in the S cluster challenge our assumptions about where star formation can occur. Surrounded by the intense gravity of Sagittarius, a star, these hot, massive stars appear to have formed in place rather than migrated from far away. Their presence hints at cold gas and dust existing surprisingly close to the central black hole, contrary to earlier expectations of a barren environment. This revelation invites us to imagine star nurseries in the shadow of a cosmic abyss. The detection of D9 suggests that black holes are not as destructive to local systems as previously thought. Even under intense gravitational stress, a binary pair can persist for millions of years before merging. This resilience highlights the delicate balance between gravitational disruption and orbital cohesion. In the cosmic theatre, even the most formidable actors do not always obliterate their companions. Gas and dust around D9 indicate that star formation may still be active near the central black hole. These materials provide the raw ingredients for new stars, hinting that the galactic center is not simply a graveyard, but also a cradle. Such duality underscores the richness of astrophysical environments, where creation and destruction are intertwined. Observing this interplay fosters a deeper appreciation of cosmic complexity. The strange G objects in the S cluster challenge our categories. They appear as nebulous clouds, yet act like solid stars, leading scientists to speculate that they are either unmerged binary systems or the debris from past mergers. These hypotheses blend the themes of youth and aftermath within a single phenomenon. They remind us that classification in astronomy often lags behind nature's creativity. With upcoming instruments, astronomers hope to examine these objects and confirm their nature. The improved resolution and sensitivity will allow them to trace motions and spectral signatures with unprecedented precision. In the near future, the secrets of the S cluster may be decoded, revealing whether planets or exotic phenomena lurk in the shadows. Such prospects excite the imagination, fueling curiosity about our cosmic neighborhood. When S5HVS1 was discovered streaking away from the galactic center, astronomers realized it would eventually escape the Milky Way. The star's extraordinary speed is a testament to the energy available in gravitational encounters near supermassive black holes. Its solitary journey across intergalactic space will last longer than human civilization. Thinking about such trajectories expands our sense of time and scale. In every Hill's ejection, the binary stars approach each other intimately before the black hole's tide intervenes. The gravitational forces stretch and twist the system, transferring orbital energy from one star to the other. At the moment of separation, one star plunges inward, while the other is flung outward like a stone from a sling. This interplay of energy and motion reveals the elegance and efficiency of gravitational dynamics. The ejected star's velocity can exceed thousands of kilometers per second, a speed beyond human comprehension. At such velocities, the star crosses thousands of kilometers in the blink of an eye, leaving the galactic disk in a few million years. Its companion, meanwhile, begins a tight orbit around the black hole, slowly spiraling inward. This divergence of fates underscores the contrast between capture and freedom in gravitational encounters. In the binary supernova ejection, the mechanism is more explosive. When one star in a binary exhausts its fuel and detonates as a supernova, the sudden mass loss causes the gravitational bond to snap. The surviving companion no longer feels the former gravitational tug and flies off at its orbital speed. This less dramatic, yet still powerful process produces runaway stars that trace smooth arcs through the galaxy. Dynamical ejections in clusters involve more complex interactions. When three or more stars pass extremely close, gravitational chaos ensues, exchanging energy and momentum among the participants. One star may gain enough energy to escape, while the others settle into new orbits or even merge. The richness of these interactions results in a variety of outcomes, from gentle adjustments to violent expulsions. When intermediate mass black holes lurk in cluster cores, their gravitational fields amplify dynamical ejections. Passing stars receive stronger slingshots, raising the ceiling on possible velocities. This synergy between stellar interactions and compact objects makes clusters fertile grounds for hypervelocity stars. Observations of such stars thus hint at the presence of hidden black holes. The theoretical maximum speed for Higgs-ejected stars can reach 4,000 kilometers per second under ideal conditions. Such extreme events would require a very tight binary approaching incredibly close to the black hole. While none of the observed hypervelocity stars reach this limit, the physics allows for such possibilities. These upper bounds help astrophysicists gauge the energies involved in gravitational slingshots. In contrast, clusters lacking supermassive black holes can still produce ejections up to 2,000 kilometers per second. This value arises from multi-body interactions and the gravitational well of the cluster itself. When a star is thrown clear, it must still climb out of the Milky Way's gravitational potential to leave entirely. Such speeds represent a significant fraction of that escape velocity, illustrating how clusters can be nearly as efficient as black holes at launching stars. Because clusters produce their fastest ejections early, the population of hypervelocity stars we observe now may represent survivors from an earlier epoch. They have had time to travel far from their birthplaces, making their origins harder to trace. This delay between ejection and detection complicates efforts to match stars with their source clusters. It also adds a time element to our study of these cosmic runaways. The speed of J0731 plus 3717 is a dramatic indicator of the forces at play in M15. Astronomers realized that only an intermediate mass black hole could provide enough gravitational kick to produce such a velocity. This detection thus acts as indirect evidence for a rare class of black hole, bridging the gap between stellar mass and supermassive varieties. Observing hypervelocity stars can therefore reveal hidden compact objects. Matching the chemical fingerprints of J0731 plus 3717 to M15 confirms its origin and supports the ejection scenario. Similar analyses applied to other high-velocity stars can help trace them back to specific clusters or regions. This forensic approach uses elemental abundances as a cosmic barcode. It transforms each hypervelocity star into a messenger from a specific time and place. Back at the galactic center, the density of stars belies the black hole's gravitational hunger. There are enough young and massive stars whirling around Sagittarius A star to build a small open cluster. Their distribution and motion provide a laboratory for testing theories of star formation and dynamics under extreme gravity. They also set the stage for potential gravitational slingshots. The observation that hypervelocity stars from the center have speeds capped around 700 kilometers per second remains puzzling. According to simple models, some should be much faster, yet we do not see them. The absence of captured companion stars near the black hole deepens the mystery. Perhaps other processes limit or modify the distribution of ejection velocities. Introducing an intermediate mass black hole into the central environment could explain these anomalies. Acting like a gravitational bouncer, this secondary object would intercept approaching binaries and moderate the energy exchange. Stars would still be ejected, but at speeds more consistent with observations. This concept is still speculative, yet it elegantly resolves two empirical puzzles at once. If such a goalkeeper existed, only a small fraction of ejected stars would surpass 700 kilometers per second, while about 10% would remain intact binaries. Observational surveys could test this by looking for pairs of hypervelocity stars traveling together. Discovering them would support the idea that not all ejections are singular events. It would also hint at a complex gravitational ecosystem near the core. The trajectory of S5HVS1 remains one of the best lines of evidence linking hypervelocity stars to the galactic center. By tracing its path backward, astronomers show it passed close to Sagittarius A star about 5 million years ago. Its speed and direction match predictions of a Hill's ejection, providing a cosmic experiment with real data. Observing such phenomena transforms theoretical concepts into tangible stories. Understanding the Hill's mechanism requires appreciating how gravitational potential energy can be converted into kinetic energy. When a binary approaches a black hole, its orbit around each other contains stored energy. The black hole's tidal field redistributes this energy, binding one star more tightly while releasing the other. This efficient transfer explains why ejected stars can achieve such incredible speeds. Conservation of energy and momentum ensures that the capture and ejection are intimately linked. The more tightly bound the captured star becomes, the faster the ejected star must travel. This symmetry underlies the predictions of velocity distributions for hypervelocity stars. It also implies that capturing an entire binary would require dissipating its orbital energy in other ways, which is rare. While the Hill's mechanism is spectacular, the binary supernova scenario is more common in producing runaway stars. When a massive star goes supernova, its companion is released and continues along a trajectory tangential to its former orbit. Such stars travel at hundreds of kilometers per second, often forming bow shocks as they plow through the interstellar medium. These quiet runaways populate the galaxy and are easier to spot than hypervelocity stars. Dynamical ejection scenarios add to this diversity, with clusters acting as gravitational pinball machines. Multi-body interactions produce a spectrum of velocities, from modest runaways to potential hypervelocity stars. The relative contribution of each mechanism depends on the environment. Understanding them helps astronomers interpret the distribution of high-speed stars across the Milky Way. Because clusters can launch stars beyond the Milky Way's gravitational grip, some hypervelocity stars may originate far from the galactic center. Determining their origins thus requires careful modeling of their trajectories, proper motions, and chemical compositions. Each high-speed star is a time capsule carrying information about its birthplace. Studying them enhances our knowledge of both clusters and the galaxy's gravitational potential. If most high-speed stars were ejected early in cluster evolution, the present population reflects events that occurred billions of years ago. The memory of those events persists in the star's velocities and compositions. This realization turns hypervelocity stars into chronicles of cosmic history. They link our current observations to the dynamic past of the Milky Way. Hypervelocity stars can therefore serve as probes to detect intermediate mass black holes, where direct observation is difficult. When a star is moving too fast to have been ejected by ordinary interactions, it points to a hidden massive companion. This method complements other approaches, such as observing accretion signatures or gravitational waves. Together, they help fill in the gap in the black hole mass spectrum. For a star to be ejected at several hundred kilometers per second from a cluster, its binary must pass within roughly 1 astronomical unit of the intermediate mass black hole. This is only the distance between Earth and the Sun, incredibly small on cosmic scales. Such precision suggests that many close encounters occur without ejection, highlighting the role of chance. When the conditions are right, however, the results are dramatic. Debates continue about whether the young stars near Sagittarius A star formed there or migrated from elsewhere. Their ages and distributions offer clues, but the evidence is not yet conclusive. If they formed in situ, it implies that gas can fall in and cool despite the black hole's influence. If they migrated, it speaks to the powerful dynamical processes that transport stars inward. The discovery of the D9 binary demonstrates that star formation and binary survival are possible even within an intense gravitational field. It suggests that the raw ingredients for stars can accumulate and coalesce before being disrupted. This example serves as a natural experiment, testing our theories of star formation under extreme tidal forces. It also hints at the diversity of planetary systems that might exist in such environments. The clear signs of gas and dust around the D9 stars provide direct evidence that material is available to form planets near the galactic center. This challenges long-held assumptions that the environment is too harsh for such delicate processes. It opens the possibility of exotic planetary systems bathed in the glow of the central black hole. Imagining such worlds enriches our sense of cosmic variety. The G objects in the S cluster may represent binary stars that have merged or are on the verge of merging. In this view, their gaseous appearance comes from material ejected during the merger or still being exchanged between the stars. If this is correct, the S cluster may host a hidden community of stellar mergers and post-merger remnants. These phenomena could contribute to the variety of outcomes near the black hole. Speculation about planets near the galactic center arises naturally once we acknowledge the presence of young stars and gas. Planets often form around such stars, and nothing in the physics prohibits them from coalescing under the black hole's watch. Detecting them will require exquisite sensitivity, but the payoff would be immense. A planet orbiting within sight of Sagittarius. A star would capture the public imagination like few discoveries have. While hypervelocity, stars like S5HVS1 embark on endless voyages, their captured companions begin new lives bound to the black hole. These stars might join the ranks of the S cluster, orbiting close enough to be subject to extreme relativistic effects. Their fates could include tidal disruption, merging with other stars, or eventual spiral into the event horizon. Each possibility adds to the tapestry of outcomes in this dynamic environment. The velocities produced by gravitational slingshots dwarf those we encounter in everyday life. Even Earth's orbital speed around the Sun, about 30 kilometers per second, is tiny compared with the speeds of hypervelocity stars. These extremes highlight the scale of energy transformations possible in astrophysics. They also remind us that the galaxy is not static, but teems with motion on all scales. The contrast between the Hill's mechanism and cluster ejections underscores how different environments shape outcomes. A supermassive black hole can propel a star at up to 4,000 kilometers per second, while clusters without such a beast max out at around 2,000. This difference reflects the deeper gravitational well at the galactic center. By measuring velocities, astronomers can infer the underlying engine. Simulations also show that some cluster ejections approach the upper limit of 2,000 kilometers per second early in the cluster's evolution. Such high speeds drop off as the cluster ages and its core expands. This temporal evolution imprints itself on the distribution of runaway stars. Future surveys may use these patterns to date clusters indirectly. A star ejected with a speed just above the Milky Way's escape velocity will slowly climb away, eventually entering intergalactic space. Its journey will last millions to billions of years, during which it may traverse dark halos and voids. Such travelers become intergalactic ambassadors of their home galaxies. Their existence broadens our conception of the Milky Way's influence. Thinking of hypervelocity stars as fossils ties them to the early life of their parent clusters. Each star's velocity is like a chisel mark carved by past interactions. By assembling many such marks, astrophysicists reconstruct the cluster's youth, much as paleontologists reconstruct ecosystems from bones. This approach demonstrates the interdisciplinary connections in science, where methods echo across fields. Intermediate mass black holes fill a gap between the well-known categories of stellar mass and supermassive black holes. Evidence for their existence remains sparse, so each detection is valuable. Hypervelocity stars offer a novel means of detection, linking dynamic events to hidden objects. This interplay of inference and observation drives forward our understanding of compact objects. The requirement that a binary pass within one astronomical unit of an intermediate mass black hole to produce a high-speed ejection sets stringent conditions. Most binaries will not approach so closely, so the events are rare. When they do occur, they produce signatures that stand out in surveys. Searching for these rare events becomes a treasure hunt in the cosmic archaeological record. Close to Sagittarius. A star, the tidal forces are so intense that they can rip apart stars that come too near. Yet, some stars dance just within the safe zone, orbiting at relativistic speeds without being destroyed. This dynamic environment is a testbed for general relativity and extreme astrophysics. Observations here refine our understanding of gravitational theory. The puzzling absence of very high-velocity stars from the galactic center invites us to question our models. Why do we not see stars traveling at thousands of kilometers per second if the Hill's mechanism can produce them? Perhaps selection effects hide them from us, or perhaps other processes moderate their velocities. Resolving this question will deepen our comprehension of the inner galaxy. Adding an intermediate mass black hole into the mix alters the energy partitioning between captured and ejected stars. It reduces the peak velocities and changes the proportion of intact binaries that survive the encounter. Such subtle changes can have dramatic effects on the distribution of observed hypervelocity stars. These scenarios illustrate the sensitivity of astrophysical predictions to underlying assumptions. According to the goalkeeper model, around 10% of ejected stars might remain bound as binaries. Observing such pairs would provide a key test of the hypothesis. These ejected binaries would be travelers carrying their own microcosm of gravity. Their detection would be a remarkable intersection of dynamics and companionship. S5-HV S1 also highlights the importance of precise measurements in uncovering cosmic stories. Its velocity and trajectory were determined through careful observations and modeling. Without this precision, it would appear as just another star among billions. But with it, we trace its origin to the very heart of the Milky Way and witness a dramatic event. The gravitational interactions that produce hypervelocity stars are deterministic yet unpredictable in detail. Slight differences in the initial conditions, such as binary separation or angle of approach, can drastically change the outcome. This sensitivity to initial conditions is reminiscent of chaos theory. It adds an element of unpredictability to the cosmic narrative. Despite this sensitivity, the process is extremely efficient at converting orbital energy into translational kinetic energy. A small change in the internal energy of the binary translates into a huge change in the velocity of the ejected star. This efficiency underscores the power of gravitational interactions as engines of cosmic motion. It also shows how energy can be exchanged without any physical contact. Understanding the relative contributions of the Hill's mechanism, binary supernovae, and dynamical ejections is an ongoing challenge. Each mechanism operates in different environments and leaves different signatures. Observational surveys across multiple populations are required to untangle their roles. The interplay between theory, simulation, and observation drives this field forward. Dense cores of globular clusters are not the only places where dynamical ejection can occur. Young massive clusters, nuclear star clusters, and even the outskirts of galaxies can also produce runaway stars. The variety of environments enriches the diversity of high-speed stars. It shows that the universe rarely limits itself to a single way of doing things. As clusters lose mass and expand, their ability to produce high-speed ejections declines. This process parallels the life cycle of organisms, beginning with vigorous youth and settling into a quieter maturity. The cluster's gravitational potential weakens, and its internal interactions become less violent. In this way, dynamical astrophysics echoes biological metaphors. The hypervelocity star ejected from M15 is a singular piece of evidence, yet it holds broad implications. It suggests that intermediate mass black holes may exist in other clusters as well. If similar stars are found elsewhere, they could signal a population of these elusive objects. Each detection thus builds a case for the missing link in black hole evolution. The ability to connect a star's chemical fingerprint to a specific cluster and to infer an intermediate mass black hole from its speed demonstrates the power of multidisciplinary analysis. Astronomers combine dynamics, spectroscopy, and modeling to piece together the story. This integration of methods exemplifies modern astrophysics. It shows that progress often comes from weaving disparate strands into a coherent narrative. The cluster around Sagittarius. A star is an example of such integration. Observing the orbits of its stars tests general relativity, reveals star formation processes, and informs theories of stellar dynamics. It is a laboratory where multiple subfields of astronomy converge. Its study enriches our understanding of both fundamental physics and cosmic evolution. Still, some puzzles remain unresolved, like the velocity distribution of hypervelocity stars. Are we missing the fastest ones because they have left the galaxy, or because they are too rare to be seen? Are there biases in the types of stars we detect? Addressing these questions requires careful analysis of both observational limitations and theoretical expectations. The idea that additional massive objects could moderate ejections demonstrates how small changes in environment can have large effects. This sensitivity encourages astronomers to model systems with increasing complexity. By including intermediate mass black holes, gas, or even multiple black holes, we move closer to realistic scenarios. Each addition shifts the predicted outcomes, guiding observational strategies. Predictions of the fraction of high-velocity stars and intact binaries provide a benchmark for observations. Surveys can compare measured distributions to these numbers and refine the models accordingly. Such feedback loops between theory and data drive scientific progress. They also remind us that astrophysics is an empirical science grounded in observation. Watching S5 HVS1 recede into the depths of space evokes both wonder and melancholy. This star will never return, and its light will eventually fade beyond our detection. Yet, its journey will continue across intergalactic distances, carrying with it a piece of the Milky Way. Contemplating such voyages expands our mental horizons and situates our home within a vast cosmos. The Hill's mechanism illustrates how local interactions can have global consequences. A small region around the black hole becomes the launch pad for stars that will traverse the galaxy and beyond. The ripple effect of these events contributes to the distribution of mass and energy on a galactic scale. It shows that, in the universe, everything is connected. The timescales involved in these processes are enormous compared to human lifetimes. The ejection itself happens in minutes, but the journey across the galaxy spans millions of years. This contrast between instantaneous violence and slow travel highlights the layered nature of cosmic events. It invites us to adopt a temporal perspective beyond our usual experience. Clusters and black holes both serve as gravitational engines, yet their scales and contexts differ. Comparing them helps us understand how gravitational potentials at different scales influence star trajectories. It also informs us about the distribution of compact objects across the galaxy. Such comparisons are fundamental to building a coherent picture of stellar dynamics. Gravitational interactions at all scales, from binary star separations to cluster-wide encounters, shape the architecture of the cosmos. They dictate the orbits of planets, the structure of galaxies, and the fate of stars. Hypervelocity stars are a dramatic manifestation of these universal interactions. Studying them thus touches on fundamental principles of physics. Observing the current distribution of high-speed stars provides a time-lapse of cluster evolution. Each star's path is like a frame in a cosmic movie, capturing a moment in the cluster's history. By assembling these frames, we reconstruct the narrative of cluster formation, interaction, and decline. This method underscores the power of stellar kinematics as a tool for understanding the past. The evidence for intermediate mass black holes from hypervelocity stars is indirect, yet compelling. By ruling out other mechanisms for the observed speeds, astronomers narrow the possibilities. Such reasoning is a hallmark of scientific deduction. It shows that, even without direct detection, we can infer the existence of hidden objects from their effects. The requirement of a close pass within one astronomical unit underscores the rarity of these events. Many binaries will orbit the cluster's center without such close encounters, and only a few will produce hypervelocity stars. This rarity means each detected star is valuable. It encourages astronomers to conduct wide surveys and to refine their detection techniques. The presence of gas and dust near Sagittarius. A star suggests that star formation processes can operate even under strong tides. This challenges earlier models that assumed the black hole would clear out its surroundings. It invites revisions to our theories of how gas accumulates and cools in such environments. It also hints at the possibility of complex feedback between star formation and accretion onto the black hole. The failure to detect captured companions near the black hole remains a mystery. If hypervelocity stars are being launched, their partners should remain in the vicinity. Perhaps they are faint or hidden by dust, or maybe they were subsequently ejected by other processes. Solving this puzzle will require deeper and more sensitive observations. A secondary black hole orbiting the primary could remove captured stars from our line of sight. Such an object would complicate the orbital dynamics and could merge with the primary in a dramatic event. This possibility connects hypervelocity stars to the broader context of black hole mergers and gravitational wave sources. It shows how different astrophysical phenomena interlink. Looking for intact binary hypervelocity stars is an exciting prospect. Detecting such a pair would provide strong support for models that predict their existence. It would also offer a unique laboratory for testing binary evolution under extreme conditions. The search is on, and each new survey increases the chances of discovery. The captured companions of hypervelocity stars may become part of the black hole's inner entourage. Their orbits will be highly eccentric and oriented randomly, contributing to the chaotic environment of the S cluster. Over time, interactions between these captured stars could lead to further ejections or mergers. The cycle of capture and ejection thus continues. Some hypervelocity stars have been traced back not to the galactic center, but to the Large Magellanic Cloud. The Hills mechanism operating near a massive black hole in that dwarf galaxy could produce such stars. Alternatively, dynamical interactions within clusters in the cloud could launch them. Tracking these stars across intergalactic space showcases the reach of gravitational processes. The possibility that one galaxy can fling stars into another highlights the interconnectedness of the local group. These cross-galactic travelers carry information about their host galaxy and enrich the stellar populations of their destination. They are cosmic migrants, bridging the boundaries between islands of stars. Their existence blurs the lines we draw around galaxies. Stars ejected from globular clusters must still overcome the gravitational pull of the Milky Way's dark matter halo. If their velocities fall short, they will remain bound on wide orbits. This requirement explains why not all cluster ejecta become hypervelocity stars. It also ties the study of runaway stars to the broader question of the galaxy's mass distribution. Gravitational interactions operate the same in clusters, galaxies, and planetary systems. They are governed by the same physical laws, scaled up or down. Hypervelocity stars are just one dramatic manifestation of these laws. Studying them deepens our appreciation of gravity's versatility. Because hypervelocity stars can travel for billions of years, they act as long-term memories of past interactions. The galaxy's dynamic history is thus written in the motions of these solitary travelers. Reading this history requires patience and sophisticated tools. It is a task that spans generations of astronomers. Each hypervelocity star detection narrows the range of possible explanations for its existence. When combined with other observations, the evidence builds a bridge between speculation and certainty. In this way, individual discoveries accumulate into comprehensive understanding. They remind us that science progresses through incremental insights. Combining kinematic data with chemical abundances allows astronomers to paint a complete picture of a star's journey. This synergy of techniques is essential when physical processes operate over vast distances and times. It shows that no single measurement can tell the whole story. Instead, synthesis brings clarity. The environment near Sagittarius. A star serves as a natural laboratory for testing extreme physics. Observing stars and binaries there probes tidal forces, general relativity, and stellar evolution. Each measurement helps refine theoretical models that apply across astrophysics. This laboratory is unique, making the galactic center a precious resource. Yet, there is still much we do not understand about the population of hypervelocity stars. How many have we missed? How does dust obscuration affect our counts? Are there biases in the types of stars we detect? These open questions maintain a sense of mystery. If an intermediate mass black hole does orbit the supermassive black hole, their eventual merger will produce gravitational waves. The detection of such waves would provide another avenue for probing the center. It would also tie together the study of hypervelocity stars and gravitational wave astronomy. This cross-pollination exemplifies the interconnectivity of modern astrophysics. Future observations will test the predicted fractions of high-velocity stars and intact binaries. Larger telescopes and surveys will expand the sample size and improve detection sensitivity. As data accumulate, models will be refined and new questions will emerge. The process is iterative and ongoing. Tracing the past path of S5HVS1 required accurate measurements of its position, distance, and motion. These measurements allowed astronomers to reconstruct its orbit backwards, like rewinding a cosmic movie. Such reconstructions demand both precise instruments and sophisticated modeling. They are examples of forensic astronomy in action. The energy source for hypervelocity stars lies in the binding energy of binaries. Breaking apart a binary releases energy stored in the star's mutual orbit, analogous to splitting an atomic nucleus. This energy is converted into motion of the ejected star. Understanding this conversion helps unify different physical processes under common principles. Just as nuclear reactions power stars, gravitational interactions can power their motion. This analogy underscores the different ways energy can be harnessed in nature. It also emphasizes the universality of conversion between potential and kinetic forms. The cosmos is a playground of energy transformations. In the binary supernova scenario, when one star explodes, the sudden loss of mass reduces the gravitational attraction holding the pair together. The surviving star then leaves its orbit and travels through space at its original orbital velocity, unbound from its companion. This process produces runaway stars that appear lonely but carry the memory of a lost partner. It adds another chapter to the story of stellar ejection. Observations of systems like Vela X1 confirm that the binary supernova scenario occurs in nature. In these systems, a massive star and a neutron star travel together, leaving behind a bow shock as they plow through the interstellar medium. The presence of such a shock provides a visual marker of the star's high velocity and its supernova origin. These cosmic wake patterns reveal the traces of past explosions. The travel times for runaway stars from supernovae can be millions of years, and their velocities, while high, are lower than those of hypervelocity stars. Nonetheless, these speeds are enough to move stars far from their birthplaces, populating the galaxy with scattered wanderers. Studying their trajectories helps reconstruct the history of supernova events and the evolution of massive binaries. It enriches our understanding of the interplay between explosive death and solitary survival. When clusters host intermediate mass black holes, they become miniature analogues of the galactic center. The gravitational dynamics scale down, but the principles remain the same. This similarity allows astronomers to test theories in multiple settings. It also suggests that nature repeats patterns across scales. Stars flowing out of clusters contribute to the diffuse halo of the Milky Way. These flows add to the galaxy's extended stellar halo, which is composed of stars from various origins. Hypervelocity stars are at the extreme end of this spectrum. Their study is part of a larger effort to map the galaxy's outskirts. As clusters lose mass through ejections, stellar winds, and supernovae, their gravitational wells weaken. This mass loss feeds the broader galactic environment, redistributing material and energy. It is a form of galactic ecology, where clusters interact with their host. Hypervelocity ejections are one channel in this exchange. Intermediate mass black holes might be stepping stones in the growth of supermassive black holes. If so, understanding them is crucial to understanding the evolution of galaxies. Hypervelocity stars provide one of the few methods to detect them indirectly. This interplay between dynamics and growth underscores the unity of cosmic processes. The masses required to produce the observed ejection speeds are in the range of several thousand solar masses. This places intermediate mass black holes in a mass regime that is hard to detect by other means. Too small to dominate their environments like supermassive black holes, yet too large to form from single stars, they remain elusive. Hypervelocity stars may be their heralds. The mixture of young stars and strong gravity at the galactic center provides a setting where multiple processes coexist. Star formation, tidal disruption, and gravitational ejection all occur within a few light years. This complexity challenges simple models and demands holistic approaches. Each phenomenon influences the others in a delicate dance. Observational biases play a role in which hypervelocity stars we detect. The brightest and nearest stars are easiest to find, while faint or distant ones may escape our surveys. This bias could skew the apparent velocity distribution. Recognizing and correcting for it is essential to drawing reliable conclusions. Gas near the galactic center can absorb or emit radiation, affecting our ability to see stars. It also interacts gravitationally with stars and black holes, altering dynamics. Including gas in models of hypervelocity ejection may change predictions. The interplay between gas and gravity adds another layer to the complexity of this environment. The predicted fractions of ejected stars depend sensitively on the initial conditions and parameters used in simulations. Changing the mass of the intermediate mass black hole or the distribution of binaries can shift the results. Thus, these simulations are not definitive answers, but exploratory tools. They help guide observations and refine hypotheses. The case of S5-HVS1 has spurred renewed interest in searching for more hypervelocity stars. Each new detection adds to the statistical sample and improves our understanding of their origins. As surveys grow, the picture will become clearer. Until then, every star counts. Even after ejection, the path of a hypervelocity star is influenced by the gravitational potential of the Milky Way. It curves gently through the halo, slowed but not stopped. Mapping these paths provides constraints on the mass distribution of dark matter. Thus, hypervelocity stars are probes not only of their ejection processes, but also of the galaxy's structure. As a hypervelocity star travels, it may interact with interstellar and intergalactic gas. Its bow shock can heat and compress the medium, leaving a faint trail. Over cosmic time, such interactions might influence the gas distribution in subtle ways. Even solitary stars can shape their environment. Energy transfer is the common thread linking all ejection mechanisms. Whether by gravitational tides, explosive mass loss, or dynamical interactions, energy shifts from one form to another. Understanding these transfers helps unify the varied phenomena under one physical framework. It emphasizes the conservation laws that govern the universe. Globular clusters are not only sources of hypervelocity stars, but also key laboratories for stellar evolution. Their age and composition provide clues about the early universe. When we study cluster ejections, we also learn about the formation of heavy elements, the life cycle of massive stars, and the interplay of gravity and nuclear processes. The story of hypervelocity stars thus intersects with many astrophysical themes. Because the fastest ejections occur early, the hypervelocity stars we see now may come from clusters long dissolved. Their parent clusters may have evaporated or merged with the galactic field. In that sense, these stars outlive their origins. They are survivors of ancient cosmic communities. Detecting more hypervelocity stars will refine our census of intermediate mass black holes. Each new case allows us to map out where these black holes might lurk. It helps build a distribution of their masses and locations. This information feeds into models of galaxy formation and growth. The synergy between detailed simulations and precise observations is essential for interpreting the data. Simulations help identify what we should look for, and observations validate or refute the models. Together, they create a feedback loop that deepens our understanding. This iterative process is at the heart of scientific inquiry. The presence of young stars near Sagittarius, a star, suggests that conditions once existed for gas to cool and collapse. Perhaps a burst of star formation occurred when a stream of gas fell into the central region. These episodes might be tied to past accretion events onto the black hole. Understanding these cycles links star formation to galactic feeding. Anomalies, such as the velocity cap and missing companions, provide valuable clues about the underlying physics. Science often advances by investigating exceptions. These anomalies challenge our assumptions and motivate new ideas. They keep the field dynamic and open-ended. A secondary black hole could have formed through the merger of a cluster or dwarf galaxy with the Milky Way. Such an event would bring its own black hole into the galactic center, where it might orbit for some time. This scenario links hypervelocity stars to the broader context of galactic assembly. It shows how local phenomena relate to global events. Testing predictions about the fraction of intact ejected binaries requires careful identification of stars in pairs. Observationally, this is challenging because binaries can be widely separated or faint. However, upcoming telescopes with higher resolution and sensitivity will make such searches more feasible. Each successful detection will inform the models. By tracing S5HVS1 back to the central black hole, astronomers confirmed that at least some hypervelocity stars originate there. This direct evidence ties the theoretical mechanism to a real event. It anchors the concept in observation and sets a standard for future cases. Others may follow this star's path in our data. The initial separation of a binary influences the outcome of its encounter with a black hole. Close binaries have more orbital energy to release, leading to faster ejections. Wider binaries may not survive the encounter or may be captured whole. These details matter when predicting velocity distributions. Orientation also matters. The angle at which the binary approaches the black hole affects how energy is redistributed. Small differences can flip a star's fate from capture to ejection. This sensitivity underscores the chaotic nature of these encounters. It also complicates the task of modeling them comprehensively. Cluster density plays a key role in dynamical ejections. Dense cores produce more interactions and more ejections. As the core expands, interactions decline. This simple relationship shapes the temporal evolution of ejection rates. A star's final fate depends on whether its velocity exceeds the escape velocity of the galaxy. Those that do will journey into intergalactic space. Those that don't will remain bound, albeit on wide orbits. This threshold transforms the classification from runaway to hypervelocity star. It highlights the importance of the galaxy's mass and potential. Because clusters can be billions of years old, the ejections we see now may have occurred when the universe was young. These stars carry information across cosmic time. They act as messengers from eras we cannot otherwise observe directly. Their stories connect the present to the deep past. Using hypervelocity stars to detect intermediate mass black holes requires combining different types of measurements. Astronomers must measure velocities, chemical compositions, and positions with high precision. Each measurement contributes to building the case. This multifaceted approach exemplifies the thoroughness needed in astrophysical investigations. The closeness of the binary to the black hole at the moment of ejection is a reminder of the scales involved. On human scales, one astronomical unit is familiar. On cosmic scales, it is minuscule. When stars brush this close to a black hole, the outcome is unpredictable. This interplay of scales is a recurring theme in astrophysics. Star formation near the black hole may feed the black hole when young stars lose mass. Stellar winds and supernovae inject material into the accretion flow. In this way, star birth and black hole growth may be coupled. This feedback loop shapes the evolution of the central environment. The absence of high-velocity stars may mean that the most energetic ejections happen infrequently. Alternatively, they may leave the galaxy too quickly for us to observe them, or be too faint to detect. Each possibility has different implications for the frequency of extreme interactions. Determining which is correct requires deeper surveys and improved statistics. The environment near the galactic center is dynamic and evolving. Stars orbit, gas flows, and perhaps other black holes lurk. Each component influences the others, creating a complex system. Hypervelocity stars are products of this system, and in turn contribute to its evolution by carrying away energy and mass. Simulations that include various components, stars, gas, black holes, yield different predictions for ejection rates and speeds. Comparing these predictions with observations helps refine the models. Over time, the models become more sophisticated. This iterative process demonstrates the synergy between theory and observation. The distance to S5HVS1 is part of what makes its measurement possible. Being relatively close allowed astronomers to measure its motion precisely. Not all hypervelocity stars will be so obliging. Many will be too far or too faint for detailed study. The Hills mechanism is just one part of a spectrum of astrophysical processes that can eject stars. Each mechanism has its own signature and range of velocities. By identifying these signatures, astronomers can classify runaway stars and deduce their origins. This classification enriches our understanding of the galaxy's dynamic processes. Ejected stars can also interact with the interstellar medium, generating shock fronts and heating the gas. These interactions can produce faint emissions detectable at certain wavelengths. Observing them provides additional context for the star's journey. It shows that even a single star can have ripple effects. Synergy between different ejection mechanisms means that some stars could be subject to multiple processes. A star might be kicked by a supernova and then further accelerated by a cluster interaction. This stacking of events complicates the narratives we try to assign. It also enriches the tapestry of stellar life. In the larger context, hypervelocity stars remind us that galaxies are not closed systems. Stars and gas flow in and out, driven by gravity, radiation, and interactions. This flow contributes to cosmic evolution on grand scales. Hypervelocity stars are participants in this cosmic circulation. Each hypervelocity star carries a memory of its origin encoded in its velocity and composition. Like messages in a bottle, these memories travel across vast distances and times. Decoding them requires both patience and ingenuity. It is a task that brings together kinematics, spectroscopy, and modeling. The detection of intermediate mass black holes through hypervelocity stars bridges scales in black hole research. It connects the small-scale interactions of binaries to the large-scale growth of galaxies. This bridging underscores the interconnectedness of cosmic phenomena. Understanding one scale helps illuminate the other. Careful analysis of the conditions needed for ejection helps identify where to look for hypervelocity stars. Clusters with compact cores and possible intermediate mass black holes are prime targets. Observations will either confirm or refute the presence of such objects. This targeted approach optimizes the search. The ability of gas to persist and form stars near Sagittarius. A star may depend on the balance between heating and cooling. Radiative feedback from stars and accretion may heat the gas, while dust and molecular lines cool it. Understanding this balance is key to explaining the observed young stars. It also has implications for star formation in other extreme environments. Detection limitations are not purely observational. They also involve theoretical expectations. If our models predict that hypervelocity stars should be extremely rare, then not seeing them may not be surprising. Conversely, if they should be common, their absence is more significant. Clarifying these expectations is necessary for interpreting observations. The idea of a gravitational bouncer near the galactic center adds a playful metaphor to serious physics. It conjures an image of stars being deflected like soccer balls by a goalie. Though fanciful, the metaphor captures the essence of the proposed mechanism. It makes the complex dynamics more accessible to the imagination. Comparing predicted fractions with observed populations will either support or challenge current models. If the numbers align, our understanding gains credibility. If not, we must revisit the assumptions. This iterative refinement is at the core of scientific progress. It ensures that theory remains anchored in reality. The demonstration provided by S5HVS1 has become a benchmark. Future hypervelocity stars will be compared to its properties to assess their origins. It sets a template for what we expect from a Hill's ejection. In this way, one star influences the study of many. Calculating the energy budgets of binary and ejected stars requires careful bookkeeping. Energy must be conserved, but its distribution changes. This accounting connects microphysics to macroscopic motions. It is another example of the power of theoretical physics to explain observations. Hypervelocity stars push the extremes of stellar motion. They challenge our intuition about how fast a star can move and still be part of a galaxy. They invite us to consider the full range of outcomes in binary evolution. Extremes often illuminate the rules of the game. The processes that launch stars across the galaxy participate in a cosmic ecology. They redistribute mass and energy, influence star formation, and shape the structure of galaxies. Hypervelocity stars are not isolated curiosities. They are active agents in galactic evolution. Their study contributes to our broader understanding of cosmic systems. From the microcosm of a binary pair to the macrocosm of a galaxy cluster, gravitational dynamics operate across scales. Hypervelocity stars provide a bridge between these scales, linking the intimate to the immense. They exemplify how local interactions can influence global structures. Their stories unify our picture of the cosmos. The cosmic memory carried by hypervelocity stars extends not only backward, but also forward. As they move through the universe, they will encounter new environments, perhaps influencing them. In that sense, they are seeds of change, carrying potential across time and space. Their journeys remind us of the continuity of cosmic evolution. Searching for intermediate mass black holes through hypervelocity stars is an exercise in detecting the unseen. It teaches us that not all discoveries come from direct observation. Some arise from the absence of alternatives. This subtlety is part of the art of astronomy. Finally, the very existence of hypervelocity stars underscores the role of improbable events in shaping the universe. Rare encounters, precise alignments, and violent explosions contribute to the cosmic tapestry. These events may be unlikely individually, but given the vastness of time and space, they inevitably occur. Hypervelocity stars are the testament to this interplay of chance and necessity. A star can drift beyond the galaxy's familiar lanes when a gravitational dance with a supermassive neighbor flings it outward like a sling. In that moment, the star becomes a vagabond, no longer bound to the spiral arms or the swirl of the disk. The encounter strips it of its companion if it had one, and the black hole captures that partner while launching the survivor into emptiness at speeds that defy ordinary reasoning. As the star accelerates into the cold, it carries a memory of the light and dust that shaped it, and it wonders what awaits beyond the edge of its home. In the solitude that follows, the star glances back at the inner city of stars from which it came, the crowded bulge with its swirling ring of gas and dust. It remembers the press of solar neighbors and the gentle tug of spiral arms, and how it once danced with a binary companion. Now it races away at a pace that only a supermassive gravitational slingshot could impart, a pace exceeding 500,000 kilometers per second. The memory of the event is a blur, but the awareness of speed lingers like a wind that never dies. B stars are blue and young by galactic standards, often 2 to 5 times the mass of our Sun. They burn bright and quick, and many of the hypervelocity stars we have found belong to this group, which makes their exile especially poignant because their lifetimes may end before they ever cross the emptiness between galaxies. When the first of their kind was detected in 2005, it was moving at more than 1.5 million miles per hour, far beyond what any ordinary supernova could bestow. That star, like our narrator, speeds toward the halo with the energy of a cosmic cannonball. To be thrown out at such a pace, a star must exceed the escape velocity of its home galaxy. Yet that escape velocity depends on where one sits within the galactic disk. Near the solar circle, the speed required to escape the gravitational grip of the Milky Way is roughly 578 kilometers per second, while farther out near 50 kiloparsecs, the escape speed falls to around 367 kilometers per second. Our wandering star moves faster still, rendering it forever unbound. That knowledge settles in like a truth from which there is no return, a quiet acceptance that the Milky Way will become a shrinking glimmer behind it. There was no single instant when the star decided to leave. The laws of gravity and a chance approach to the galactic center sealed its fate. As part of a binary pair, the star may have brushed dangerously close to the central black hole, and the resulting three-body exchange captured its partner and imparted energy to the survivor. Hills predicted such ejections decades ago, and the discovery of HVS-1 confirmed the theory. Now countless stars with similar fates may be speeding through the halo, most of them invisible to our eyes. As the star rockets away, it might carry with it a retinue of planets, moons, or asteroids that were once bound to its gravity. If those worlds exist, they too feel the jolt, and they cling tightly to the star as it tears free of the galaxy's gravitational potential. Life on such worlds, if any arises, would witness the longest of nights as the star drifts away from the luminous canopy of the Milky Way. The sky would slowly empty until only the faint glow of the galaxy remained, a thin band of light receding into the darkness. Far behind, the star leaves the bustling disk where star formation is common and new suns ignite in clouds of dust and gas. It leaves behind the spiral arms dotted with stellar nurseries and open clusters, and the rich reservoir of interstellar material that shaped its youth. The star also leaves behind the heavy elements that future generations of stars will inherit. Now its course takes it into a region where such comforts are scarce, and where the interstellar medium thins to almost nothing. Within the first million years of its flight, the star passes through the thickest parts of the stellar halo. This halo is a roughly spherical region surrounding the disk and bulge, filled with old, metal-poor stars known as Population 2. It also contains globular clusters, ancient spherical assemblies of stars that orbit the galaxy like distant satellites. The density of stars here is far lower than in the disk, and there is little gas, so the star soon finds itself navigating a much quieter environment. Dark matter dominates the halo, outweighing the visible stars and gas, and shaping the gravitational potential of the galaxy. Though this dark matter is invisible, its presence makes itself felt in the way the star's path curves. There is also a tenuous corona of hot gas extending far into the halo, detectable only through emission lines and X-ray observations. The star can sense this gas as a faint breeze, and sometimes its outer atmosphere interacts with it, shedding a trace of material that leaves a spectral signature behind. In the stellar halo, the star encounters ancient globular clusters that contain hundreds of thousands of stars. Their orbits carry them far above and below the disk, and they are relics from the early days of the galaxy. The star may pass near one of these clusters, glimpsing a concentration of old suns bound together by gravity. The sight is both comforting and alien, for these clusters are far older and redder than the bright star itself. Further out, star formation has ceased, and the halo population is stable and quiet. The star notes that many of the objects it sees are low in heavy elements, reflecting a time when the universe was young and metals were scarce. The halo's rotation is slow, only about 50 kilometers per second around the galaxy's center, far less than the rapid spin of the disk. This slow motion accentuates the sense of time stretching out as the star moves beyond the realm of its birth. Despite the halo's calm, the star is aware that its velocity outstrips that of everything around it. It passes other stars as though they were standing still, its speed a remnant of the encounter that set it free. There is no friction in space to slow it down, only the gradual pull of the galaxy's mass distribution, which weakens with distance. Once the star has travelled far enough, that pull can no longer rein it in, and it continues on a trajectory that will eventually carry it between the galaxies. As the star leaves the last vestiges of the disk and bulge behind, it enters the tenuous outer halo, where the density of stars declines steeply. Here, the B-type stars it encounters are rare and out of place, because there is no active star formation in this region. When astronomers detect such stars, they suspect an exotic origin, like the one our traveller experienced. The star feels kinship with these other blue wanderers, each on its own path away from the galaxy. It is in this region that escape velocity falls below its cruising speed, meaning that the star is truly beyond the gravitational grasp of the Milky Way. The concept of escape velocity is subtle. There is no single threshold that applies everywhere because the Milky Way's mass is not uniform. At the solar circle, the escape speed is high, while farther out it drops, and the star's survival beyond it depends on the distribution of visible and dark matter. For our traveller, this moment arrives with a softening of the Milky Way's pull, and an awareness that the home galaxy is now a background object. In the halo, the star also encounters occasional clouds of gas that belong to the galactic corona. These clouds are mostly hydrogen and helium, heated by past accretion events and shock waves, and they are so diffuse that their densities are less than 1 particle per cubic centimetre. When the star's light passes through one of these clouds, it leaves subtle absorption lines that astronomers can study to understand the halo's composition. In this way, even a solitary star becomes a probe of its environment. From its perspective, the star watches the Milky Way gradually shrink. The spiral arms become indistinct, the bar and bulge merge into a glowing core, and then the galaxy fades into a faint, flattened ellipse. Beyond this, only the halo remains visible, a diffuse glow of ancient stars, and a ghostly halo of dark matter that cannot be seen directly, but is inferred by its gravitational effect. The star feels a mixture of sadness and wonder as it leaves the only home it has ever known. As the star moves deeper into the halo, its velocity relative to the surrounding stars remains high. If it possessed any planets, those worlds are now companions in exile. They are bound tightly to the star by its gravity, but they too will experience the changing sky and the gradual dimming of the Milky Way. On those worlds, the nights will grow long, and the view of the galaxy will slowly contract, teaching any observers about impermanence and the vastness of the cosmos. After tens of thousands of light years, the star enters a realm where the halo's ancient clusters become infrequent and interstellar clouds are rare. Dark matter still surrounds it, but this invisible component offers no comfort. The star is alone with its light and the gravitational bond it shares with any companions. The path ahead leads toward intergalactic space, and the star cannot help but anticipate what lies beyond the halo's edge. In this transitional region, the star senses that the gravitational pull from the Milky Way continues to drop. The escape velocity here is a fraction of the speed at which it travels, and so each passing million years carries the star ever further from the galaxy. Its path is not a straight line, for the gravitational influence of the Milky Way, and perhaps the local group, will slightly bend it. But the direction is clear, outward into the cosmic ocean beyond. At some point, the star may cross paths with another exiled star, or a runaway ejected from a satellite galaxy. Their meeting is fleeting, because relative velocities are high, and space is vast. Two hypervelocity stars passing within a few light years of each other would be a rare coincidence. If it happens, the moment would be like two comets in an immense dark sphere, each with a story of ejection and a future of unbounded travel. Eventually, the star reaches the outermost halo, a region where dark matter still dominates, but where visible matter is almost absent. There are still population 2 stars here, but they are few and far between. Globular clusters are more distant, and the star rarely sees more than a faint glimmer from a neighboring sun. The sense of isolation deepens, preparing the star for what comes next. As it passes beyond the orbit of the last satellite galaxies, the star enters the true intergalactic medium. Here, the density of ordinary matter falls to roughly 1 hydrogen atom per cubic meter. That is a vacuum so empty that a human-designed vacuum chamber on Earth seems dense by comparison. The star feels the emptiness as a silence, as if space itself has turned into a whisper. The intergalactic medium is not completely empty. It is filled with hot, ionized gas, mostly hydrogen and helium, heated by gravitational collapse and cosmic shock waves. This gas is tenuous, but over cosmic distances it accumulates. When the star's light passes through these atoms, it can be absorbed at specific wavelengths, leaving faint imprints that astronomers detect as absorption lines in the spectra of distant quasars. In this way, even the emptiest spaces speak through the language of light. Between galaxies, space is also permeated by the cosmic microwave background radiation, a relic from the early universe that fills every corner of the cosmos. This radiation is faint but omnipresent, and it bathes the star and any planets in a soft glow that cannot be seen with the eye. Dark energy also becomes more important out here, accounting for most of the universe's energy and driving the accelerated expansion of space. The star feels no force from this mysterious component, but its environment expands gently around it, widening the gulf between the Milky Way and itself. The cosmic voids that the star will traverse are not entirely featureless. Faint filaments of dark matter and clouds of primordial gas thread through them. These structures are the skeletons of the cosmic web, the scaffolding upon which galaxies and clusters formed. Occasionally, tiny dwarf galaxies or globular clusters reside in these filaments, shining weakly against the darkness. To the star, they are like lanterns in a desert night, far apart and seldom visited. Being in intergalactic space means leaving behind the notion of a local neighborhood. Distances between objects are measured in millions of light years, and the likelihood of encountering another star becomes vanishingly small. The star knows that if it once had planets, or even smaller companions, they will continue to orbit, but they will see nothing but the faint afterglow of the cosmos. There is no interstellar medium to supply new gas or dust, so the star and its planets must rely on their internal reserves. Every journey through the void is a lesson in perspective. The star sees the Milky Way as one among billions, a luminous spiral suspended in an almost empty expanse. With time, the galaxy will fade into a small patch of light, then into a memory. If the star carries with it a species capable of thought, those beings might look up and see only one major galaxy in the sky, and never know that their world once belonged to another cosmic city. Around the star, the temperature of space is close to absolute zero, except for the faint warmth from the cosmic microwave background. Any planets orbiting the star rely solely on the star's radiation to maintain warmth. Should the star eventually exhaust its nuclear fuel and become a white dwarf, its planets would freeze in the unending night. Even a luminous star cannot warm space beyond its immediate surroundings, and so the void remains cold and indifferent. The star travels through an environment dominated by dark energy, dark matter, and trace amounts of baryonic gas. Cosmic rays and neutrinos pass through it without resistance, and the star's own radiation travels outward, attenuating with distance. On large scales, the gravitational influence of the local group gently guides the star's path, but over billions of years, even that influence will wane. The star is truly a cosmic orphan, moving under its own inertia through the fabric of space-time. Although the star is alone, it shares its fate with countless other objects that wander the cosmos. Rogue planets, unbound by any star, drift through the galaxy and beyond in the dark. These worlds may have formed around stars and then been ejected, or they may have formed on their own from collapsed gas clouds. Estimates suggest there could be billions or even trillions of them in the Milky Way alone. They are hard to detect, but their presence speaks to the prevalence of exile in the universe. Microlensing surveys have detected hints of these free-floating worlds. Early studies suggested there might be about 2 Jupiter-mass rogue planets for every star. Later studies revised that estimate downward, but still point to a significant population. In 2020, astronomers even found evidence for a rogue planet with a mass similar to Earth using microlensing. These techniques rely on the gravitational bending of light when a massive object passes in front of a background star, briefly amplifying its brightness. The star may one day pass near such a rogue planet, though the odds are incredibly low given the vastness of space. If their paths align, the planet might feel the star's gravity and be captured, joining the star in its journey through the void. Alternatively, the star might pass close enough to alter the planet's course, changing its fate forever. These possibilities, while remote, add a layer of intrigue to the star's lonely voyage. Interstellar visitors occasionally cross the paths of stars and planets, and some of these wanderers have been observed in our own solar system. In 2017, astronomers spotted an object named Oumuamua, meaning a messenger from afar arriving first in Hawaiian. It moved at nearly 196,000 miles per hour and did not show the typical behavior of a comet. After passing the Sun, it continued on its trajectory out of the solar system, leaving behind only questions about its nature and origin. 2 years later, a second interstellar object was discovered, Comet 2, I/Borisov. Unlike Oumuamua, this object showed clear signs of cometary activity, with a coma and a tail. It travelled through our solar system at about 110,000 miles per hour. Observations from the Hubble Space Telescope revealed dust around its nucleus, and later a fragment appeared to break off. After its brief visit, it too continued on its way back toward interstellar space. These interstellar objects remind us that the space between stars is not entirely empty. They may have been ejected from distant planetary systems or formed in isolation in the outskirts of molecular clouds. Their high speeds mean that they are not captured by the sun's gravity, and instead they follow hyperbolic paths through the solar system. The star sees them as fellow travelers, each with its own story of origin and journey. A recent discovery hints that even stars with planets can be cast into intergalactic space. Astronomers using microlensing identified a feeble star that appears to be moving at least 1.2 million miles per hour, with a planet orbiting at a distance comparable to the gap between Venus and Earth. If confirmed, this would be the fastest known exoplanet system, and its speed may be enough to escape the Milky Way's gravitational pull. The system is thought to have been ejected by interactions with the galaxy's central black hole, just like solitary hypervelocity stars. The planet, a super Neptune, clings to its star as they both head toward intergalactic space. The star reflects on these cosmic companions, rogue planets, interstellar comets, and runaway stars with their own planetary systems. They are all part of a community of exiles, each pushed or pulled away from their birthplace. Some carry with them the potential for life, while others are barren chunks of rock and ice. Together they form a hidden population that threads through the galaxy and beyond, unseen except for brief moments when they cross paths with observers. While traveling, the star wonders how astronomers on distant worlds might detect its passage. It knows that its light carries information about its speed and direction. The color of its light shifts slightly toward red because it is moving away from observers. This is known as the Doppler shift. By comparing its spectrum to reference spectra, astronomers can measure this shift and determine the radial component of its velocity. Radial velocity alone is not enough to fully chart the star's path. Astronomers also need to know how the star moves across the sky, which is called its proper motion. For stars in the halo and beyond, this motion is extremely small, often less than a millisecond per year. Measuring such tiny shifts requires instruments like the Gaia spacecraft, which can detect minute changes in position over time. When both radial velocity and proper motion are measured, the star's three-dimensional motion can be reconstructed. Gaia's precision astrometry has opened a new era in the study of hypervelocity stars. For most bright stars, it can measure radial velocities to within 1 or 2 kilometers per second, and for fainter distant stars, an accuracy of 5 to 10 kilometers per second is sufficient. Gaia also records proper motions and distances, enabling astronomers to trace trajectories backward to their points of origin. In the case of hypervelocity stars, this origin often lies near the galaxy's central black hole, confirming the Hill's mechanism as the likely cause of their ejection. Spectral lines provide additional clues. In the red part of the spectrum, strong lines like the calcium-2 triplet are used to derive radial velocities. Even for metal-poor stars, these lines remain prominent, allowing accurate measurements even with moderate resolution spectra. When the star's light is split into its component colors and analyzed, astronomers can see shifts that reveal not only its motion, but also its temperature, composition, and age. The star's identity is encoded in its photons, and those photons carry a message across vast distances. Hypervelocity stars like our traveler often show radial velocities hundreds of kilometers per second above the typical speeds of halo stars. In a sample from the HVS survey, stars with speeds about 100 kilometers per second above the escape velocity were likely ejected from the galactic center. Others, with slightly lower speeds, might be runaways from the galactic disk, or even from the Large Magellanic Cloud. The distinction between these populations helps astronomers understand the dynamics of our galaxy and the frequency of extreme events near massive black holes. The first hypervelocity star, known as HVS1, was a main sequence B star with a mass about 3 times that of the Sun. It had a velocity exceeding 670 kilometers per second in the galactic rest frame. Such a speed is about twice the local escape velocity at its distance of 100 kiloparsecs, making it unquestionably unbound. Observers concluded that only a gravitational interaction with the central black hole could have launched it, confirming theoretical predictions. The star senses that its own velocity is similar to those of known hypervelocity stars. It wonders whether astronomers have noticed it, plotted its trajectory, and traced it back to the center. The star's spectral trail is faint at such distances, and its proper motion is small, making detection challenging. Yet with each passing year, Gaia and future missions improve the sensitivity of our instruments, bringing more of these cosmic travelers into view. As astronomers accumulate data on these stars, they refine models of the Milky Way's mass distribution. Escape velocity measurements help constrain the total mass of the galaxy and the distribution of dark matter. The presence of unbound stars at certain distances implies a certain depth to the gravitational potential. and by studying their velocities, scientists can estimate how much unseen mass must be present. In this way, hypervelocity stars become probes, not only of the Hill's mechanism, but also of the structure of the entire galaxy. Proper motion measurements have historically been obtained with the Hubble Space Telescope, but Gaia has expanded the sample dramatically. In a recent study, Gaia provided proper motions for 39 out of 42 known hypervelocity candidates, with errors as low as 0.11 milliseconds per year for the brightest stars. Those measurements allowed researchers to compute trajectories and distinguish between stars ejected from the center and those ejected from the disk or other galaxies. The star thinks about how its own motion might be catalogued someday by a distant civilization. For now, the star leaves behind a trail that we can detect only indirectly. Its light carries a record of its journey through absorption lines imprinted by the halo and intergalactic medium. It may also interact with the tenuous gas in the void, leaving behind subtle emission or scattering signatures. These clues allow observers to reconstruct the star's path long after it has passed, and to imagine the forces that set it in motion. Despite the science behind its discovery and detection, the star's journey is also a story of endurance. It will spend millions of years traveling through the halo, and then billions more crossing the space between galaxies. Even if it burns out before reaching another galaxy, its momentum will carry it forward as a white dwarf, or perhaps even a black dwarf in the distant future. Its story is a testament to the extremes of cosmic dynamics. In contemplating its fate, the star reflects on the concept of escape itself. In physics, escape velocity is the speed needed to break free from a gravitational field without further propulsion. For the Milky Way, that speed varies depending on the distance from the center and the distribution of mass. Our star's velocity exceeds the escape velocity at its current location, which means that no amount of gravitational pull from the Milky Way will bring it back. Escape is permanent in this context, a one-way journey. Stars, like planets and comets, have surface escape velocities as well. For a typical main sequence star, the surface escape velocity is around 600 kilometers per second. The Hill's mechanism can impart velocities nearly twice that, up to about 1,370 kilometers per second. Those speeds are necessary for a star to leave the galaxy entirely, and they exceed what most other astrophysical processes can produce. Our star, propelled by such an encounter, is one of the rare few that achieve these speeds. The idea of a star surpassing its own surface escape velocity is fascinating. It suggests that the gravitational energy of the encounter with the black hole was channeled into kinetic energy. The star does not disintegrate because the energy is delivered to its center of mass rather than its surface. As it leaves, it retains its integrity, carrying with it any bound companions. The star thinks of this as a gentle yet irrevocable push. In the outer halo, the escape velocity continues to drop with distance. At 50 kiloparsecs, the escape speed is about 367 kilometers per second, much lower than the speed of our star. Beyond that, the gravitational field of the Milky Way becomes weaker and merges with the gravitational influence of the local group. By the time the star reaches intergalactic space, the Milky Way's pull is a faint echo, and local gravitational fields dominate only when the star passes near another galaxy. For many stars, gravitational interactions with smaller objects, such as supernova explosions in binary systems, can impart high velocities. These runaway stars can reach speeds of hundreds of kilometers per second, but they are usually bound to the galaxy. Unbound runaways are rarer and require extreme circumstances like those near the galactic center. Our star knows that its own speed makes it part of this elite class of cosmic escapees. The speediest of hypervelocity stars approach or even exceed 1,000 kilometers per second. These velocities correspond to over 2 million miles per hour, a pace at which the star could travel from the Earth to the Moon in less than 15 minutes. Yet in cosmic terms, such speed still translates into journeys that take millions of years to cross the distances between galaxies. The scale of space dwarfs even the most extreme velocities. As the star contemplates distances and speeds, it also considers time. B stars live for only a few 100 million years, while smaller stars can live for billions. If the star is indeed a B star, its luminous phase may end long before it leaves the local group. It may spend most of its intergalactic journey as a white dwarf, cooling slowly over trillions of years. Even as a glowing ember, its momentum will carry it onward. Life on any planets orbiting such a star would experience a dynamic environment. Initially, the star's brightness would sustain conditions for life if the planets were at the right distance. But as the star ages and its luminosity changes, those conditions would shift. Eventually, the star's evolution would strip away its outer layers, and its planets would face freezing temperatures in the intergalactic night. The prospect of life evolving under these circumstances remains speculative but evocative. One can imagine a civilization developing on a planet orbiting our exiled star. Early in their history, they would see the Milky Way as a prominent band dominating the night sky. Over generations, that band would narrow and fade. Stories would be told about the ancient world from which they came, perhaps recorded in myths or legends. The shrinking galaxy would become a symbol of both their origin and their separation. At some point, the Milky Way would be too small to resolve with the naked eye from their world. The galaxy would appear as a faint smudge, then a point of light, and finally nothing at all. Without powerful telescopes, future generations might not even know of its existence. Their cosmology would be shaped by the emptiness around them and the few galaxies they could see. The star's exile would have become their normal,